See, this time it did turn off my camera and my mic. I just don't know what the rhyme and reason is for my mic and camera to be turned on or off when I start the recording. All right. Welcome everybody to Office Hours. This week we are mostly going to be doing practice problems and preparing everybody for the upcoming exam. I think it's this coming Thursday. I will be covering as many problems as I can today. If I don't get to all of them, I will consider adding a second office hours this week. It might be Monday or Tuesday night, depending on how far I get and how much time I think I need. But let's see how far we can get. In order to keep the schedule a little bit tighter today, we have so many problems to go over. I do want to express a few rules that I normally, I normally am okay with answering all questions, but I want to limit them a little bit today. So I don't want to answer questions about the material too much. I want to focus on the practice problems and the solutions to the practice problems. I don't want to answer too many questions of, oh, what if we change this aspect of the problem? Or, oh, what if the graph was directed instead of undirected? Those take me a second to kind of consider and come up with a solution, and not all the students are interested in it. And sometimes I might get stuck because, I'm trying to solve the problem that you just gave me live, and I want to try to get through these as quickly as possible. And I am going to limit how much students can ask about their own solutions. So I know that a lot of students like to, say, oh, I see your solution, but I solved it a different way. Or I see your solution, but for whatever reason, I want to solve it in a slightly trickier way with this work. If you want to do something like that, feel free to post it in the practice problem threads. There are other TAs, other students, myself, I might venture in there and take a look and answer those questions. But I think we should just focus on, one solution per problem today, just so that we can get through these. Okay. All right. Any questions before we start? Okay, cool. So I am not going to do 3.1 nor 3.2. I went over how DFS works and running through DFS on a previous week. So I think that's just something you need to practice. So feel free to do it yourself and then post on the practice threads and see what other students get. But I don't think it's really like critical for me to go over it again. So I'm going to skip 3.1, 3.2, and let's see what 3.7 is. Okay, let's do 3.7. So 3.7, and I think specifically we're asked to do A, B, and C, A through C, yeah. All right, so a bipartite graph is a graph, G equals BE, whose vertices can be positioned into two sets, where the union is your set of vertices, and they don't share a vertices, so the intercept between the two sets are non-existent, and such that there are no edges between vertices in the same set. For instance, if U and V are part of subset V1, then there are no edges between U and V. So what that looks like is basically, and I'm sure you've seen this before. If you don't know what that is, let me see. Okay. So you basically have vertices like, separated on two sides. And of course, this isn't how like the graph needs to be drawn. It just means that you can separate your graph into bipartite sets, and you have like this why is this? My tool is misbehaving for some reason, and I don't know why. That's weird. You can imagine that this set Okay, I think this tool got itself updated. Okay, you can imagine this set is in this set of vertices is partitioned into one set, and this set of vertices partitioned into a second set, and then there can be edges between these two sets, and those edges can be set up any way you want, but uh, vertices within the same set do not have edges to each other. So as long as you can take a graph and you can separate it into these two subsets of vertices, and all vertices has to be accounted for. You can't just have like a vertice like outside here by itself. It has to be in one of the two sets, and then there's no edges between any two vertices in the same set. Then you can consider the graph to be a bipartite. Okay, so give a linear algorithm to determine whether an underarc graph is bipartite, and then yeah. So I'll give my solution for that, and then we can talk about it. And I think a student asked the other day, is a CNF or two-set algorithm only used for doing CNF? And yes, it mostly is. But if you can reduce a problem to a CNF, then a two-set, then you can use a two-set algorithm to solve that problem. And that's what actually what we do here. So this one's actually kind of a little funny because you're taking a graph problem, you're reducing it to a CNF, and then you're using the two-set algorithm, which is another reduction going from going from a two-set to a graph problem as part of the algorithm. So you're going from graph to two-set to graph to end up solving it. Okay. So the way we're gonna do this is that we're gonna take the graph, and we're going to construct a two-set CNF of it. So for every edge that we have UV, we are going to say, we're going to set up two clauses saying U or V and not U or not V. Okay. We'll go over why in a second. The way I like to write my solutions is that I like to just give the steps of my algorithm completely, not writing down why I'm doing this. Because I feel like that way, when I go to write the correctness, I have my frame of mind saying, okay, I'm going to explain my entire algorithm all at once, rather than try to do it throughout my algorithm. Because if I do that, sometimes I might miss a detail of like, oh, in my mind, I already said why I did this, but I actually didn't, and I forget in my correctness. Or the TA might mix algorithm steps and your correctness explanation, and then you don't get all the points. So what I like to do is I like to completely separate the two. So my steps will be like, won't tell you any reason why I did it. So then we run the CNF through the two-set algorithm and get back assignments. If the CNF has a satisfying assignment, we return true. Otherwise, we return false. Okay, so that's real simple algorithm. But the part that makes it work is what's interesting. So if U and V share an edge, then they must be in different sets, right? So we drew this diagram up here. Like if these two were to share an edge, they couldn't be in the same set. If these two share an edge, they must be in two different sets, right? That's the rule of a bipartite graph. So the CNF forces the following, right? So by setting the CNF, or this two set right here, we're saying that if U is true, right? So if U is true, then not U is false. And if not U is false, then not V must be true. And if not V must be true, then V must be false, right? This is the implications that we showed when I went over the two-set algorithm last week, right? So getting those two implications, now we say by setting up all our edges into this two-set, right? We have to find an assignment that no two endpoints of an edge are both true or both false, right? So what you basically are doing is that saying, well, if a vertex is set to true, right? The true literal is set, then it's on the left side of the bipartite. If it's set to false, then it's on the right side of the bipartite. And so as long as a single edge aren't both true or both false, you've encoded into your two set that they cannot be in the same subset. And if they can't be in the same subset, and you go through all your edges and you code them all out, and you're able to divide up every single endpoint, every two endpoints of every edge into the two different subsets, then you have a bipartite graph. And that's what the logic behind this is. So then creating the CNF is O of n plus m. You for every edge, you have to create this. It's actually, I think this actually can be O of, no, it has to be O of n plus m because you have to account for any vertex that that doesn't have an edge. So like if I had a vertex out here by itself, that also has to be part of your CNF. So it's O of n plus m. And then running the two-step algorithm is an O of n plus m. And so the overall takes O of n plus m. Okay, so that is the algorithm needed for part A. Any questions about this so far? Mahmoud?
Yeah, sorry. When you say has a satisfying assignment, that means there's no like there's no edge that goes from like you to you, like you trace all the way back. There's no looping, is what you're saying,
No.
right?
So when we say a satisfying assignment, when you give a CNF to a SAT algorithm, such as 2SAT, you either get back assignments that says, okay, in order to satisfy all your clauses, here's what you have to set each literal to. Or the 2SAT algorithm might come back and say, I can't find a satisfying assignment. There's too many there's contradictions or conflicts within your clauses that forces it not to be satisfiable. So any satisfying assignment means I can take all the true statements, put it one side, all the false statements, put it on the other side, and know that there's no edges between the subset of vertices among themselves. If the 2SAT algorithm comes back and says I can't make a satisfying assignment, that means that at some point I have let's say 3 vertices that can't be divided into the 2 sides because they form a triangle. So there's no way to separate them into two parts.
Okay, I think I understand. Thank you.
Okay. Karishma?
Hi, can you hear me?
Yes.
So for the two-set, when you're creating the CNF, are you saying that all falses have to be in one partition and when trues have to be in another partition?
Yep. That's exactly
Uh,
what the 2SAT algorithm with this setup will do.
So how exactly are you specifying which one is a true and which one is a false? And I understand that it comes from the two-set, but I guess I'm not understanding how you mapped this to the CNF. I'm not understanding that connection.
Okay, so I don't actually have to do any assignment. The question is merely, is this graph bipartite? And so if I can divide them into 2 subsets such that they don't share an edge within the subsets, then it is bipartite. So that's all I'm asking. I don't really even care what the assignments are. I'm just saying true if I can find a satisfying assignment, false otherwise. The way that the clause is set up is using this to represent every single edge. What this is saying is that if U and V, right, are both true, this like if they're both true, then this setup of clauses is going to fail.
Because it'll be in
Okay,
one partition.
right. So if these are both true, then these are both false, and this side will fail. Now, if they're both false, it'll also fail. So if they're both false, then this side will be satisfied, but this side will not be satisfied. So the only way for both clauses to be satisfied is that one vertex is true and the other vertex is false. And that's the only way. And that is exactly what we're trying to do with the bipartite. We're trying to say that of any given edge, one vertex can be in one subset and the other vertex is in another subset. And that we can do this for every single vertex and edge in relationship to the whole graph, and we can find a satisfying assignment.
So we don't have to actually know how it's being partitioned into the two subsets.
No, not in this question, not in this particular question.
Okay.
Okay. All right, I'm gonna answer one more question so that we can move to the next part. Manjanatha?
Yeah, hi, Joves. So I'm trying to get the intuition behind the two SAT, and when I was trying to solve some of these problems, I was going from implication graph back to the CNF, kind of working backwards towards CNF. But looks like I may not be able to do it for the bipartite if I go through the implication graph. Is there any way to do that to get to that solution?
Sorry, I'm not understanding the question.
So here the U or V, and when we draw it into an implication graph, that is not U implies V and not V implies U. That's how the implication
Oh,
graph
yeah. I mean, that's how the two-set algorithm works. It's not, you don't just take that and translate directly to this problem. You want to take your problem and encode it into a two-set CNF and then tell the two-set algorithm to solve it. That's how you use the two-set algorithm. You want to encode whatever problem you have into a logic into a logic of literals and clauses, and then just tell the two-set algorithm to solve it for you.
Right. That is internal part of it. Yeah. So to come to this form of the CNF, like, and then given a bipartite graph. So I did not understand how you converted from that bipartite graph to this kind of assignment. You might have already covered it, but it was not very clear to me.
Yeah. So I think it's a mistake to go into this thinking, I have a bipartite graph. How do I convert it to a CNF? What you want to do is take a graph of unknown, you don't know whether it's bipartite or not, and you want to convert it to a CNF such that when the CNF is solved, you can use that to answer whether the graph is bipartite or not. And all I did was say, okay, well, I need my two vertices to not be in the same set in some way. And so this is a way to force that into the CNF, is saying, I can't have both vertices be true. I can't have both vertices be false. One has to be true. The other has to be false. And if they are, if all my vertices can be divided that way, then I know I have a bipartite. If my vertices cannot be divided that way, I know I don't have a bipartite. You're not taking a bipartite and converting it to two-set CNF. You're doing just a normal graph to a two-set CNF and then seeing if it's bipartite.
Okay. Thank you. That's good.
All right. Yep. All right. I'm going to move on to part B and C. So part B is asking, there are many ways to formulate this property. Yep. For instance, an undirect graph is bipartite if and only if it can be colored with two colors. So this is a different way to answer the question. So the first way, is using the two-set algorithm. The other way is that we can use a coloring problem, coloring solution. Now, the coloring solution is actually the most direct and popular approach to this, but the coloring solution requires you to be able to modify DFS or BFS. And since we don't allow you to modify black boxes, the two-set solution is basically the most correct way for in our class to solve the problem. But if you were to just code this up, you would use it as a coloring problem, which, if you are interested, go look up 2 coloring, 3 coloring, 4 coloring. It's an interesting class of problems. You will possibly see them again when we hit NP complete. But so part B is basically saying, okay, we can also re-ask this, like summarize this question as being a two-color question, right? So what it's saying is that if I could color, and the way two-set questions are, is that if you can take a graph and you can color it into 2 colors, such that no two edges, no two endpoints of an edge have the same color, then it is a valid 2-color graph. Okay. So basically, if let's say we do blue and red and blue. So if I start off with this red, okay, this is red, then my next color is going to be blue. So this is blue. So we're happy with that. And then we go, okay, now we go back to red and blue and so forth. Okay. And so if at any point in our graph when we're trying to do this, if we find out that we have an edge that connects 2 red vertices, then we can't do 2 coloring of this graph, right? And it's really easy to see if you have a triangle of vertices that are all connected. This fails the 2 coloring test. right? You cannot color the vertices such that no two adjacent vertices are the same color. You just can't, right? Hopefully that's clear. And you can also look at this triangle, immediately say this cannot be a bipartite graph because there's no way to divide these vertices into two subsets such that no two of them share the same edge, right? So it is both not bipartite and cannot be two-colored. Now, we're trying to say that the two are related, and how do we explain that? Well, you can say that any long cycle can be separated into two sets by using different color on each neighbor, right? So like if you have a single path, or like a single path that isn't a cycle, it doesn't matter how long that path is. You just do every other color and you're great, right? You're never gonna end up circling back to the same color, and so there's no conflict. But if there's a cycle, then any even cycle can be separated into two sets because each neighbor can be a different color, right? So this is a odd number cycle, but if it wasn't odd, if we instead had a even cycle, right? Right? Then coloring this is actually quite easy. We just color every other vertex a different color, and it's okay. And this works out for all even cycles, right? For every even cycle, you just divide, you just go every other color, and there won't be a repeat. So that means that any time that you have an odd cycle, then you fail to be able to do two coloring, and that corresponds to it not being bipartite. Okay, so if we are, so the question B is saying, prove that the following formation undirect graph is bipartite if and only if it contains no cycles of all lengths. So I've shown that no cycles is bipartite, so that's fine. I've shown that even cycles are bipartite or two-colored, so that's fine. And I've shown that a odd cycle is not bipartite and cannot be two-colored. Okay, so using the above, if we were to insert an odd vertex into an even cycle, then you immediately cannot color using two colors. Okay. I'm going to get through part C real quick and then answer questions. All right, so part C is asking, at most, how many colors are needed in our undirected graph with exactly one odd length cycle? So you only have one, right? You don't have a bunch of cycles that's tangled up. Only one of your cycles is odd. And so as you can see, if I had that, all I need is one extra color. That's it. So you just do your every other color, and then the one vertex that would be neighbor to both a red and a blue, you just cover a color yellow, and that's your third color, and you're done, right? So you only need three colors. Now, if you have multiple odd cycles, you may have conflicts here and there, but in a graph that only has a single odd cycle, then three colors is enough to color the graph. Okay, so this is how you go from one sort of domain of graph problems, which is bipartite, and how it shifts into the coloring problem, and you kind of use the information that you know about one to kind of answer questions on the other. All right. Mahmoud, question?
Yeah, sorry. Going back to part B real quickly. I understand the second part where you were saying if you have an even cycle, it can be separated into red, blue, for example, and then putting a dot to connect to make like an odd cycle would not allow because you would be bumping into either a red or a blue,
Right.
which makes sense. So I got that part. It's the part before it that I struggled with a little bit, where you're going from bipartites can't have like the step before that is what I'm struggling with. Sorry.
So consider what how bipartite and coloring problems are related. A bipartite is saying that no two edges in the same set, no two vertices in the same set share an edge, right? A coloring problem is saying no two vertices of an edge have the same color, right? And so all you have to do is understand that if you subset all your red vertices and subset all your blue vertices, and they're two different colors, then they also are bipartite because none of the red vertices are going to have an edge between them because that would break the two coloring requirement. And so no two blue vertices are going to share an edge between them. And so they are basically the same thing. So a bipartite is just saying, let me separate my vertices such that none of the vertices within the same subset share a edge. And two coloring is saying, let me color my graph into two separate colors such that no two vertices of an edge share the same color. It's a 1-to-1 like mapping of the problem. It's just a different way of asking the question.
I think I get it. I'll rewatch, and if I have any questions, I'll post on it.
Yep.
Thanks.
Sounds good. Yep. All right. We're going to move on to the next problem. What is the next problem? Let's see. Okay, so 3.8 is pouring water. I really hate pouring water as a problem. I will answer this pretty quickly. We would not give a problem like this on the exam. It's just asked in a really weird way. So those of you familiar with the Die Hard movies, I think this was one of the Die Hard movies, which is you pour water. It's a like math brain teaser. All right, so I'm just gonna post the answer right away because I'm just gonna explain this. Don't worry about how you would formalize this on a test. We would not ask a question like this on a test. It's just, I thought something you should think about and understand. Okay, so we have three containers whose sizes are 10, 7, and 4, respectively. The 7-pint and 4-pint containers start out full of water, but the 10-pint container is initially empty. We are allowed to one type of operation. You pour the contents of one container into another, stopping only when the source container is empty or the destination container is full. We want to know if there's a sequence of pourings that leaves exactly 2 pints in the 7 or 4-pint container. Okay, so you want to model this as a graph problem, and then you want to use an algorithm to solve the problem, and then you want to find the answer by applying the algorithm. Okay. Part C, I think, is actually left out. Do we ask it in? Oh no, we asked the whole thing. Okay. Well, you guys can do this because it's annoying and I don't feel like it. All right. So basically what you want to model it is you want to connect the different possible outcomes of a given vertex to its as a neighbor, right? So you start off with some amount that the problem gives you. So you want to be amount of 10, 7, 4-pint containers, right? So they have to add up to 11 since we start with 11 pints of water. And then you start off with a vertex that says it, let's say, starts off with which one's a full? All right, 7, 4, and 10. Okay, so we start off with a vertex like this, 7 out of 7, 4 out of 4, and 0 out of 10. Okay, so this is what our first vertex looks like. This is a vertex, okay? And then it's just a state diagram, basically. And you want to say, okay, well, from here, I can pour the 7 into my 10 as a single action. So we have 0 out of 7, 4 out of 4, and 7 out of 10. Okay. So that's another vertex. And you can draw edges back. So this can actually go back to this one. That's allowed. Another one that we can do is we can do 4 out of 7 because we're going to pour the 4 into the 7. And then this would be 0 out of 4. And then this would still be 7 out of 10, right? So that's another. And then this has an arrow over here. And then this also can go back, right? So you just end up writing out all these drawing out all these vertices, creating this graph, and that tells you what transitions you can go from one state to the other. Okay. There are many ways to determine these values, but one such way is to take the current configuration, add a neighbor, and you just pour it away, and then you just create it. Okay. So at most there's 6 neighbors, right? Because each there's a combination of pouring from one to a second container. And if you are able to pour from one container to any of the other 2 containers, that's 3 times 2 gives you 6 possible neighbors. Okay, so at most you would end up with, I don't know how many combinations there are, but should this map. Now, the question now is to answer from the 074 in the, oh, okay, I did this backwards from what I wrote, but from the 074 configuration to start, can we get it reach a vertex that is some number 2, some number, or some number 2, okay, where star is any number. So that just means like, can I get to a configuration that I have 2 points in either the 4 or the 7 containers? It turns out that as you write out the graph, you don't need a second algorithm to do this, because the moment you get to a state that you know comes off of where we started, and you write that state out, then yes, you can. Okay, you don't need the second part. But for the sake of completion, once the entire graph is constructed, you start at 074, and then you can either return true the moment you reach one of those vertices with BFS, and then if we do not reach one by the end of the BFS run, we return false because no such configuration has reached. This was written by me before we I realized we couldn't do any sort of black box modification. So in that case, you just run BFS, and then you just look at all the vertices that are all the configuration that's allowed, and then you see if they're visited. I mean, if the distance to that vertex is not infinite, and if yes on any of those vertices, then the answer is true. Okay, and so that's 3.8. Any questions on 3.8? Mahmoud?
So I know this is not going to be on the exam, but I just wanted to make sure I understood. There's no way to do this with the black boxes. We have to make our own algorithm, so to speak.
You do use a black box, right? You use BFS after you've created the graph. So creating the graph is the main part of this, but then running BFS afterwards is just the black box. Yeah.
Thanks.
Problem. Right. Next problem. 3.11. Some of these problems I'm reading like kind of live, so I'm deciding whether I want to answer them or not as I look at them. Oh yeah, 3.11 is fun. Let's do 3.11. I think a student actually asked this in one of the threads. And I decided not to answer them because I knew that this is a practice problem we'll end up having. Okay, you're looking for a linear time algorithm which, given a undirected graph G and a particular edge in it, determines whether G has a cycle containing E or not. Okay, so you don't need to know the rest of the cycle. You just want to know if E is part of a cycle. Okay, and the way you do this is you have to understand what a cycle means to an edge. Any edge within a cycle means that from the 2 endpoints of that cycle, there is an alternative path to those from one vertex to the other, because there's a cycle, right? So a cycle means that the path between the 2 vertices of that cycle are not unique, right? Because if it was unique, then you wouldn't have a cycle. You wouldn't be able to find an alternate path, right? So that's what you're looking for. Now you're giving an undirected graph, so keep that in mind. So if you look at this, right, if we have this edge right here, okay, and I don't know what the rest of the graph looks like, but let's pretend that there's some amount of vertices like this, etc. Boom, we have a cycle. Okay. What does it tell us? Well, it tells us that if we were to remove this edge, there must still be a path from these 2 vertices. Let's call them U and V. Okay. But if there wasn't a cycle, if it wasn't part of a cycle, right? So if we were to remove all this, and I remove that edge, it means that you cannot reach V anymore. Because if you can still reach V after I remove that edge, then there was an alternate path to begin with. But if you cannot reach V after I remove that edge, that means that was the only way for you to reach V, and therefore there's no cycle. Okay? So this is the solution. Okay. We're going to remove the edge, and then we're going to run BFS from U. Check if U can still reach V. If it can, then E was part of a cycle. If it can't, then E was not part of a cycle. And the reason is, by definition, if E was part of a cycle, then there exists at least 2 unique paths from U to V, right? One with E, the edge that we want to consider, and one without. Okay. When we remove it, we have removed at least 1 unique path. And if there still is another path from U to V, then there's at least, there were at least 2 paths to begin with, and therefore it's part of a cycle. If we cannot reach from go from U to V without E, then that was the only path that exists, and therefore it was not part of a cycle. Okay, so removing E is O M. Running BFS is O n plus M, and therefore your overrun times O n plus M. Okay. The other thing is that you could technically say that removing E is O of N. That's fine too. If you were to do it from an adjacency list, you know what the first, you know where U is in your adjacency array. So you go to U in O of 1, and then you either go down however many edges there are or how many vertices there are in order to find V in U's adjacency list. All of N, either one is fine. I like to use all of N when I'm dealing with edges and all of N when I'm dealing with vertices because I don't want to think that hard about it. But if you were to argue that this took all of N, you'd be fine too. Especially because we don't know which one's bigger. All right. Eduardo?
Yes, I know you said, to not discuss other approaches. To me, just looking at this intuitively, I thought applying DFS would work just because it erases the extra thought of removing an edge and seeing if it still reaches U to V. I thought that in DFS, if it has a back edge, then you know that it has a cycle. So again, intuitively, that's the way I thought of it.
That back edge from a DFS run, that back edge from a DFS run can be any edge on that cycle. That back edge would not always show up as the UV edge. And if that's the case, like if you just ran it and for whatever reason DFS decided to create a back edge at like WX, you will not be able to determine that looking at UV, right? Because the back edge is just the first edge that ends up being part of the cycle, right? And so if I had UV and I had, like I was saying, I had like some kind of cycle, right? Your baggage could potentially exist over here. How would you know that this baggage is associated with this edge?
Did you check if the back edge is coming from V in this instance?
Well, it doesn't have to come from V. It doesn't have to come from V. The second that there's a back edge way outside of this, like where UV is connected to, like this back edge can exist from anywhere on the cycle. You'd have to have a way to associate this back edge with your UV edge to say that this back edge causes a cycle that contains UV. Right. So if you don't have a way to do that, then you haven't used this package to identify that UV is part of a cycle. You identify the cycle, sure, but how do you know that UV is part of that cycle?
Got it. All right. Thank you.
Yep. All right. So that is 3.11. 3.16 is the next problem. Cool. All right. Suppose the CS curriculum consists of n courses, all of them mandatory. The prerequisite graph G has a node for each course, and an edge from course V to course W if and only if V is a prerequisite for W. Find an algorithm that works directly with the graph representation and computes the minimum number of semesters necessary to complete the curriculum. Assume that a student can take any number of courses in one semester. The running time of your curriculum should be linear. Okay. So a few things that this problem doesn't tell you, but you can kind of infer it. One, your graph is going to be a DAG, right? Because if you run into a situation where a prerequisite of a class has to circle back to another like prerequisite, like if I have a class here that's, you know, is the prerequisite for this class and the prerequisite for this class, and somehow this class is a prerequisite for this class, you can never find a way to enter into one of these classes because you will always have a prerequisite that you cannot take, right? So you cannot have cycles in this graph, otherwise it doesn't make sense. So this has to be a DAG. Okay. The second thing that you want to consider is that you're not looking for a shortest path. You're actually looking for a longest path from the first class in a series of classes until the last class in the series of classes. Because you can't take any of those classes together, you have to take them one after another. Now, if you have a series of classes that takes 10 semesters to finish, and you have a series of classes that takes 8 semesters to finish, you can put gaps into those 8 semesters, but you still need 10 semesters to finish that, you know, string of 10 classes, right? So your time to complete the degree is gated behind your longest chain of classes, which has prerequisites. Anything shorter can be taken concurrently with a really long series of classes and be completed in time. Also, the other thing you have to consider is that if you have a class that is a prerequisite for 2 classes, which can happen, and the prerequisite for this class, and let's say this is a prerequisite for this class, right? Like that. Ultimately, these don't really matter, right? You still have to take 1, 2, 3, 4 semesters to finish. These classes can be this class has to be taken before this one, but this one can be taken any time. You don't have to take this on the 3rd semester. You can take this on the 4th semester if you want to, right? So it's ultimately this longest string of classes that we care about, even if other classes are share prerequisites with it. Okay. So what are we trying to answer here? Well, we're looking for the longest path. Now, if this wasn't a DAG, if this was a general graph that's allows cycles or an undirected graph, the longest path along within a graph is actually a NP hard problem to solve. But solving the longest consecutive path on a DAG is actually linear time. I'll give you the solution to that, and then we talk about it. Oh, another thing to understand that is that linear time in this class, or not in this class, linear time for graphs is O of n plus n, or anything lower than that. So O of n is considered linear time, and O of m is considered linear time. Okay, don't be tricked by the fact that n squared greater than m, and so you're just like, okay, well, okay. This right here, if your runtime depends on O of n squared, it is not considered linear time. This is not linear, okay? Even though n squared is greater than m, this is not linear. It has to be in terms of n or m or both, okay? This is not okay, not linear, okay? So let's go with our solution. So you're going to topologically sort your vertices using DFS, okay? And that gives you just say, okay, now I have a source I know I have a source vertex and I have a sink vertex. I want to start with the source vertices first. I know all my source vertices are going to come before all the vertices that it points to, and nothing before it will no vertex that points at that. A topologically sorted DAG goes from left to right, where edges go from the left vertex to the right vertex if there's an edge, right? So it's important to get these topologically sorted so that we can keep track of our prerequisites. Right. And then it's actually a dynamic programming problem using the graph structure. So we start with the first vertex. So we know this is a source, and for each vertex, it has an edge to increment the end vertex by 1. Okay, so what we're going to do is we're going to keep track of our classes. We're going to say, where can I write this? Right here? Yeah. Okay. Okay. We start off with the idea that if we don't have to, we have no prerequisites, it would take us 1 semester to complete all the classes. Okay. Now, we're going from left to right. For each vertex, it has an edge to increment the end vertex by 1. Okay. Go to the next vertex u, and then for all the vertices view that u has an edge to, if the count of v is less than or equal to u, then set the count of v to u plus 1. What that's saying is that, okay, so I started at 1. Okay. What are my two classes that require my A class to be done? Well, it's B and C. Okay, so B and C now becomes 2. Okay, do that. It becomes 2 because I have to take A in order to take B, and also to take C. Now, each of those are going to be 2 semesters before I can finish that class. Okay, now let's go to the next one. Let's try with I guess B. Sure. So B is a prerequisite to D. So we're going to take the number of semesters we need to finish B in order to take D, and we add it to the D. So we can say, okay, we need to take 2 classes before we can take class D, and therefore it takes 3 semesters to complete class D. Okay, let's go to C. C is going to increment D and E by 1. Now, C would increment D by 1 if the count at C was less than, the count at D was less than or equal to the count at C. What this does is to say, well, I need to take 3 semesters to complete D because of B. I also need to take 3 semesters to complete D because of C. Therefore, I don't increment this because this number here is less than this. This is already going to account for these 2 semesters that I take C. And that tells me I can take B and C together and then take D on my 3rd semester. So that's fine. E is going to say, okay, well, it takes 2 semesters to do E, and I need 1 more semester to do E. So this is going to go up by 1. So that's also going to be 3 semesters. Now we get to D, and we say, okay, what class comes after D, which is F. F takes 1 semester to do. D takes 3 semesters to do. So we add it to this, and we say it takes 4 semesters to complete all the prerequisites plus take F. E has nothing to follow it, so this is the minimum number of semesters I need to finish all the classes. I need 1 semester to do A, I need 2 semesters to do B and C, 3 semesters to do D and E, and finally a 4th semester to complete F. So now I just want the maximum number. Takes the most semesters to complete the prereqs for will be what ends up deciding how many semesters we need to complete. So it's actually this one right here. I need 4 semesters to finish my degree. Okay. This is equal to the longest path in our DAG. Our algorithm finds this longest path, and the length of the path is a number of semesters need. Okay, so that's our correctness. Okay. And so I'll read the rest because I kind of jumped around. So we know that the prereq is a chain, therefore there can be no cycles. And since there's no cycles, the graph is a DAG. Okay, we talked about that. Since it is a DAG, we can tuple sort it. Okay. So why am I doing a tuple sort? Well, because I know it's a DAG. Why is it a DAG? Well, because I had logically speaking, it has to be a DAG. And then from there, why do I do this, +1 thing? Well, I'm trying to find the longest chain, and that's what our algorithm does. It adds 1 every time I find out that I have something before early in the chain. Okay, so DFS is O of n plus m. Finding the longest path is also O of n plus m because I'm only going through each vertex once and following every single of its edges once. So I considered this vertex 1 time. I considered this edge and this edge. I considered this vertex, I considered this edge. I considered this vertex, I considered this edge and this edge. This vertex, I considered this edge. So I'm basically traversing the full graph from source to sink, and that's O of n plus m. and then finding the largest count. So I kept this array. Now I have to go and check out how many semesters I need to in order to complete that class. That's O of n, and so the over runtime is O of n plus m, and that's a linear runtime. Okay. All right. Mahmoud.
Yeah. Sorry, I have two quick questions. First one, couldn't we just use the topo sort black box in the situation? We don't have to do DFS. We just use topo sort.
Yeah, there's a lot of ways to like say you're doing tuple sort. If you want to say, oh, I'm just going to run the tuple sort algorithm, that's fine. If you're going to say, oh, I'm going to run the DFS algorithm and then use the tuple sort output, that's fine. Either way you want to say it, we allow it. It's kind of like not very clear how tuple sort is treated in the lectures, so you can use it as a black box or use it as an output of DFS, and we'll accept both.
Okay. So that was my first question. My second question is, I know you said we wouldn't discuss alternative solutions, so if you think this is not worth it, go ahead. But would there be a easier way of doing this with BFS, where you just find the maximum distance in BFS, or is there like a pitfall in using BFS for this?
You can, in fact, use BFS. That is an alternative solution, but there's a lot of setup for BFS because you can have multiple sources, and BFS only has one source, right? So like this, my graph could potentially have this, right? So now you have to find the sources. You have to run BFS in such a way that it accounts for that. So there's a lot of setup. I don't want to get into it, but it is
okay. So there's a
solution.
potential for multiple sources. Okay, that's why. Okay, good to know.
Yeah.
Thank you.
Yep. And tuple sorting accounts for the multiple sources, and it's fine. All right. Lanfen.
Hi, yeah. So when I look at when you count how many classes for each prerequisite for each A, B, C, D nodes, so I'm thinking for class D. So why don't you just use because the last layer is B and C, right? There are two prerequisite classes before D. Can you just say you have to have like a maximum the classes before D? For example, if B has three classes need to be taken, and the C has four classes need to be taken, then that means D, he has to take like four classes before he take the class D. Because he always need to get the maximum the prerequisite classes before that, right?
Yeah, but the way you would have to phrase that would be really more difficult because D doesn't know what classes point at it, right? So when you look in the adjacency list, you can't go to D and say, well, every class that points at me, I take the max of that number. Well, now I have to like go and figure out what vertices point at D, and that's not like a simple like thing you can just explain away. Like you'd have to do some graph reversals where you have to like keep track of it. You could, but I don't think that's much easier to say.
Okay, thank you.
Because at D you don't know what vertices are pointing at it, right? That's one of the issues with trying to find sources and things. Like it's not super easy. All right, Bing.
So in the exam, if we have similar setup or anything that the problem context implies that if it's not a cyclic, it wouldn't make any sense. We can assume it's a cyclic, right? As long as we in the correctness justification say, like for example, like this one, if there is a cycle, the prerequisite doesn't make any sense because you can never complete any class, right?
If you are given the graph directly, we will give you all the properties that we think you need to solve the problem on the graph. So like if you're given, MST problem, we will tell you that it has weights, and here's the input for the weights. If we don't give you any restrictions on that, we will either give you the correct restrictions or the restrictions won't matter, or you should just assume there are no restrictions. So in case of say an MST problem, we give you an array of weights. We don't tell you if it's negative or positive. You should assume that it can be either because there's no restriction added to it, right? But you can assume that the MST graph is we are going to say undirected, but you can also assume that it's undirected. It is limited by the problem statement. On a problem that maps real world objects, you can make I think obvious assumptions, or you can at least reason it out. So you can reason out that this doesn't have cycles because it wouldn't allow you to take a class if there was cycles. If I give you a graph of roads, you can assume the weights are going to be positive because negative distance roads
Do not make any
doesn't make sense.
Yeah, yeah.
Right. If I tell you a road is, the roads have direction or not, right? Or one, like I think Computopia says one-way roads. You can reason out that one-way roads means that it is directional. Some students will try to get really cute about it and says, well, you can technically walk the other way of a one-way road. And we'd say, yeah, you technically can, but very realistically, you just got -4 on your solution. I'm sorry.
Okay.
Don't try to be funny. Don't try to be cute about it. Just, I mean, we don't state our problems to trap you. Make logical assumptions that make a lot of sense when mapped to the real world. And in this case, if there's a cycle on your prerequisites, you cannot take the class, and that wouldn't make any sense on this problem.
Yeah, you basically any class on the cycle just doesn't make any sense, right? You cannot start anywhere. Okay, yeah.
Right, exactly.
But is that wrong if I say that if there is a cycle, then let's say, what if I run SCC first? Basically, I do a cycle detection first, and they say if there is a cycle, then it's infeasible. And then if it's not, then we can assume it's a DAG. Will we lose points for doing that, or is that okay?
You will not lose points for that. So one, as long as you do something that doesn't impact your overall solution being correct. Two, as long as you don't do something that would harm your runtime. Now, if you run an algorithm to detect cycles first, and it's all of n plus m, and then your overall runtime is still all of n plus m, you're safe. If you run an algorithm that doesn't, that detects for cycles, that isn't all of n plus m, and the problem clearly shows that it shouldn't have a cycle to begin with, you've just wasted runtime, and that would impact your grade.
Makes sense. Okay, thank you.
Yep. Especially since, like, if for some reason there wasn't an SCC algorithm, like let's say the SCC algorithm runs in all of n squared, and this problem says that it has to be linear, you've already broke the restrictions or broke the requirements.
Makes sense. Thank you.
All right. One more question, and then we're going to move on. Manjanatha?
Joves, can there be a configuration where there are multiple source vertices? And if that is the case, then it becomes, your step 2 will become non-linear to walk all the independent source vertices.
My algorithm accounts for multiple sources because I specifically say that if that when you do an incrementation of number of semesters to take, if we do a less than equal to check. So like if C has let's say that E has another source like this, right? G comes before E, let's say right here, and G is 1. This 1 is going to compare against this E that's 3, and it's not gonna increment. Or if we had considered G first, because G is a source and it can be at the very start of your topological sort, and we start E as 2. After we take C, which has to come before E, when we go into we check E, we go, oh, my 2 is equal to my my E, which is at 2, right? And so I'm going to increment it by 1, which is, where's my step? If V is less than or equal to U, then set the count to, yeah, so it'll be equal to it. So then we set it to be C plus 1, which would make it 3. So this algorithm accounts for multiple sources just by treating them as possible moments to do an incrementation.
True. So I was looking at one of the example or a possible configuration where you have an inverted tree where you have multiple leaf and then you keep on decrementing, right? So even if that is the case, you're visiting all the edges, so it will become log m time log m time to pass through all the edges, isn't it?
Nope. Passing through all edges takes m time. I have m edges. I take m time to pass through all edges. I also have to check all vertices, which takes n time. Therefore, my runtime for this is all of n plus m.
All the edges. Okay, yeah. Thanks.
Yep. All right. Next problem. 3.22. What is 3.22? Given the efficient algorithm which takes as input directed graph G and determines whether or not there's a vertex S from which all other vertices are reachable. Oh, from which, okay. And it's a directed graph, yep, okay. This one's pretty simple, so I'm just gonna post the whole solution. It determines whether or not there is a vertex S. Okay. All right. It's not as simple as I thought. I misunderstood. I misread the question when I'm going over it. I do have the correct solution. I thought that that V was given to you, and that is a rookie mistake because I'm pretty sure when we did give this problem to students, some students thought that S is given to you. So you're not being asked if S can reach all vertices, a specific S can reach all vertices. You're being asked if a vertex exists such that it can reach all other vertices, but you don't know which vertex could be it. Okay, so this is the algorithm to do it. So what we're going to do is going to run the SEC algorithm on G. Okay, and we're going to get back the meta vertices of an SEC algorithm. So we check to see if this SEC metagraph has a single source. Okay, if there's an SEC with no incoming edges and that there's only one such SEC. To do this, we and this is the I think I went over this a few weeks ago on how to find single source SEC. I actually don't like this way to do it, but it's the way a lot of students find easier to understand. So we create an array representing each SEC node, and then we set the value to false. Then we go through each edge in the SEC metagraph, and then for each edge UV, we mark V as true because it indicates an incoming edge. Okay, and then you just check to see if at the end there's only one false in your in your array, and if that's true, then that you only have one source because you only want one source, and there's only one source to return true, otherwise false. And so the correctness is that if there's only one source, then the source can reach all vertices because that's what a source does. A source reaches other vertices, and no vertex can reach the source, right? So if there's only one source and you have no other sources, then that source has to be able to reach everything else. And so then any vertex in that source SEC would be a candidate for S because any vertex in the source SEC can reach all the other vertices in the source SEC, right? So that's good. And then it can reach all the other SECs, so that's also good. Then there you go. But if there are two or more sources, SECs, those vertices, because no SEC can reach a source SEC. If you have two source SECs, they can't reach each other, and therefore you don't have the requirements for a vertex to reach all the vertices. SEC algorithms of n plus m, checking for the source SECs of n plus m. The way I like to check for source SECs is to reverse the graph. So in this case, reverse the SEC metagraph and check to see if there is more than one sink. Because a sink SEC in the reverse graph is a source SEC in the original graph, and if you have one sink in the reverse graph, then you have one source in the original graph, and so that answers the question the same way. Maybe I'll rewrite this to do that. I just like doing the reverse better. It's easier for me to explain. I hate this whole like, oh, keep track of an array and all that stuff. It's just confusing to me. Let's answer questions. Lemon?
There we go. Can you hear me?
Yeah. Yes.
Okay. Just a quick question. So to find out if I had a single source, I used DFS on the metagraph and then check if it was one single component. Would that also work?
Sorry, say that again.
I said I ran DFS on the metagraph and then checked if there was only one component across all the nodes. Would that also work?
No. I mean,
That would not work.
no. I mean, if you ran
Oh, sorry.
the SCC algorithm on the metagraph, you're just going to end up with the same metagraph.
On the starting from the source of SEC that I received.
You can't tell the SCC algorithm where to start running itself.
Okay.
So yeah. Now, what you can do is there's an alternative solution to this, which I'll post, which I think is what you were trying to do, but it's not with DFS.
Is it the solution with
is-
BFS?
Yeah, solution
Oh,
would be
okay.
with BFS. Yeah. So what you do instead, if you wanted to do it that way, is you just pick any vertex in the source SCC. So you're guaranteed that the first meta vertex is a source. And so if you run BFS from that source SCC, if it can reach all other vertices, then you only have one source. If it cannot reach all the vertices, then you can't, right? So that's basically doing the same thing. So that's allowed. Okay, Mahmoud?
Awesome. Thank you.
Yep.
Just wanted to confirm my understanding when you said reverse. So we reverse the graph, and then we check the adjacency list for any vertex, so to speak, that doesn't have any edges. Those are considered sources in this particular instance.
Those would
and
be
that's what
sinks.
you mean by reversing.
Those would be sinks in the reverse, but sources in the original.
Yes.
Yep.
Just
Yep.
making sure I understood the logic behind it because I was struggling for a second there.
Yep. Okay. The cache.
Hey, I want to go back to that question about DFS. So once we run the SCC and we have the metagraph, we find the source node on the metagraph, not on the original graph, but the source node on the metagraph, which is basically the last node, I believe, because it is sorted sync to source. And then we run DFS from that node on the metagraph. If they all belong to same component, CC num1, then true, right? Then the answer should be true.
DFS does not have a source vertex to run DFS from. So you can't just say run DFS from here. Not really. I mean, in some cases you can, because you can order your vertices before you give it into DFS. But in general, we don't want you doing that. So I don't think that's a good approach.
I think it states in the black box though that you can pass a starting vertex to DFS, at least in the post.
Okay, then let me see. If that's the case, then I apologize. Okay, yeah, we give it as an option. Yep. So if you want to do it that way, and you want DFS from the starting vertex, and everything is one CC num
on the metagraph.
Yeah, that's fine. Okay. Lianfen?
Yes, I want to understand if I understand correctly about your solution. So step 2, you said pick any vertex in the source SEC. It's original, the meta graph, right? And run BFS from this vertex and check if all vertices are reachable using the distance array. So do you mind just give me some like more explanation on this? Like how are we gonna do this, implement that? Like You know, BFS will just count layer by layer, right? So first layer and second layer going forward. And then using the distance array. I didn't get the idea very well. So can you just help me
So
understand that
the
better?
idea is that you can either do it on the metagraph itself or the original graph. It doesn't really matter which one. So you take a vertex that you know is in the source SEC, or you do it on the source SEC itself in the metagraph, and you run BFS. And you're saying, okay, well, if a vertex within the source SEC can reach all the other vertices, then I don't have another source, because if I had another source, then that vertex would not have been able to reach it. So that's the thing you're answering, is that can a vertex in a source SEC reach all the other vertices? And BFS does that for you, because when BFS can't reach a vertex, that vertex is infinite, right? So you just run BFS and says, find all the vertices that are reachable, or find out if there's any vertices that are not reachable.
Okay, so other than that, I think I heard you mention that there might be like a multiple source component in the
Right. So
SCC.
if you have two sources, then running BFS starting from one source SCC can't reach the other source SCC. And so if that's true, then you have vertices that's not reachable. And if you have vertices that's not reachable, then the answer is false.
Okay, I understand. So that means when you say way in the source SCC, it could be like a multiple source SCC, right? It's not necessary for the unique as a source SCC.
I'm just saying in the source SCC here, I don't even tell you like which one. I don't even say how to identify the source SCC. Again, I could be a little bit more restrictive. Take the first pick the one meta vertex that you know is a source SCC and run BFS from there.
Okay. Thank you so much.
Yep. All right, I'm gonna move on to the next problem. So that was 3.22. 3.24. Okay, so so you're giving linear time algorithm following task. So you have a DAG, okay? Does G contain a directed path that touches every vertex exactly once? Okay, that means that you have a path that goes from a initial source to a sink, and you go all the way through, and you don't have to double back or seek an alternative path. Now, this question following 3.22 can be a little tricky, because students you'll say, okay, well, if I have one source and one sink, then I have a path. That is a requirement, but that's not the only requirement, because if you have one source and one sink, and then you have a bunch of vertices right here, okay, your assumption would be, well, if I just check that I have one source and one sink, then my pathing has to go this way, right? And therefore I have a path that goes all the way through. But that's not actually the case, because even with a single source and a single sink, okay, this is a graph that has a single source and single sink, and you cannot get a path that goes through every single vertex, because when you come here, going this way skips this vertex, and going this way skips this vertex. Okay, so that's not what you're trying to do, and so a single source and single sink can't. What you want to do is you want to know if, after you've tuple sorted your vertices, whether there is a single path that goes from everything on the left to the next vertex on the right. So you want to know if there's an edge that goes like this. Okay, because if any time there is an edge that's lacking, it means that this skip has occurred. And the second that you have this skip occurring, where this vertex does not have an edge next to the immediate next vertex, it means that you have a possibility of a fork. So you want to check whether every single adjacent vertex has an edge to the next vertex. Yeah. And so that is our solution. Paste it here. Okay. So we're going to run a topological sort. And this is an example how I say run the DFS-based topological ordering algorithm. Sometimes I'll say, oh, run the topological ordering algorithm. Sometimes I'll say run DFS and take the topological ordering from that. You can do either. It's okay. We allow it to be a separate black box. We also allow it to be a consequence of DFS. We denote this array as T with n vertices. Okay, so because we have to keep track of this. This array is sorted from source to sink. That's a fact. And then we're checking. And you don't have to do this with like mathematical notation. You could have just done this more narratively. Check if T of I plus 1 is a edge for all vertices. And if this is true, then you return true. Otherwise, you return false. Okay. Step 1 is a known algorithm, get the topological ordering of DAG, because we want this. And so now that we know this ordering, we want to know if there's an edge between every single vertex from beginning to end. If for some reason you're missing that that vertex, that edge, then we cannot reach the neighbor from the previous, and our path must backtrack to an earlier point to reach T plus 1. So that's where the fork happens. And so we don't have a directed path that can reach all vertices. Running DFS is open plus M. Doing the check, because you're going to go through all your vertices once, and you're going to consider all the edges at most once. It's open plus M, so your solution is open plus M. I'm actually going to rewrite this answer. I actually don't like this one. Give me a second. Let's do it live. Let's do it together. Right. This is where I keep all my notes. This is the infamous Joves notes that ends up getting talked about. I used to release this. I don't anymore because I write down the solutions to every problem, and then students just use it to write their own solutions, and it's unfortunate. But it is like 90 pages worth of solutions that I've written. So let's get rid of this. I don't like this. Okay, so from source to sink, that is a previous column. That's fine. If a vertex does not have an edge to the vertex 3, All right, I like this better. More narrative, easier to read. Let's go with that. Two. All right, I'm happier with the solution. Questions, Spencer?
Hello, sorry.
Yep.
So would then proving this also mean that there is like one unique topological sorting for this?
Yes, that's exactly it. So if so it's an if and only if a DAG has a single path that touches all vertices, if and only if it has a unique topological sorting. Yep.
Cool, thank you.
Yeah. Sato?
Yes, so for this solution, can we, after running the topological sort, can we actually run DFS from the source node and actually check if the post numbers are in decreasing order of increment 1? So like 10, 9, 8, 7, 6. There's no skipping.
No, because even though we're checking to see that every edge follows, you can actually have an edge right there. I'm sorry. So you can actually have an edge right there, and these other two blue edges are allowed to exist, right? And so you possibly could, DFS could possibly be like, okay, well, I'm going to take this edge and do this, and then double back, and then do this, and double back and do this, and that's fine. That's allowed, but it doesn't tell me if this series of edges exists just by running DFS and post numbers.
Oh, okay, thank you.
Yep. Bing?
Hey, I just have a question about the runtime for the check the immediate next node's edge's existence. So I know we can index directly to the linked list for the vertex, the outgoing vertex, right? But based on the common runtime post, it takes ON to check if that edge actually exists or not. But since we need to repeat that for every single vertex, wouldn't that be ON square rather than ON plus M? I'm just trying to reconcile how do we perform a check that still performs in linear time? So it's O1 to index to the linked list for the outgoing vertex edge list, right? And then it's ON to find if that edge exists or not, because we may have to iterate through all of them.
Right. So this is the case where you have to consider how edges relate to each other, right? You can and this is why I say it's okay to say by the way. If I look at it as an O of n, what I'm saying is that a single vertex can have most n minus 1 edges. I can only have edges to every other neighbor and have n minus 1.
Right.
Right. But at the end of the day, I still have only m edges across all my
that
vertices.
makes sense. Okay.
Right. So all combined, it's I know it's like a really hard thing to like explain. That's why in this case, to go through all edges, it's always O of m. But worst case, you can do O of n, but you have to like consider that like it's not O of n squared when you go check every vertex because you can combine that into O of m. That does say though that O of n squared is the upper bound of O of m. So yes, it could be O of n squared, but that's if you have like a worst case like.
Makes sense.
Okay.
Yeah, it's because you have to be worst case for every single vertex to reach that. Yeah. Okay. Makes sense. Thank you.
Can you just help me understand better? So why is that when you check the following edge will be OM instead of ON for each node?
Yeah. So So if I have my okay, if I have my thing here, right? Okay, so this can have up to n edges, right? And this can have up to n edges, and this can have up to n edges. Okay. So you could potentially say that at the worst case upper bound, you have O of n squared edges.
Is it m
check.
edges? Because n is number of vertices, right? Not number of edges.
Right, but it is n because each vertex can have up to n minus 1 neighbors. So it's like it's n minus 1.
Okay. Okay.
Yeah. So it's n O of n squared because you have that. I mean, that's completely large. But we say this is why we want to use m as much as possible because m represent how many edges there are. So even though this is our super upper bound, we can also say this is O of m edges. And m is like some, right? And so m is the tighter bound because m can be much smaller than n squared. Okay.
So
now
m represent the actual edges number, right?
Yeah, the actual number of edges. Because
okay.
m is less than n squared. Now, if you don't trust the TAs on why m less than n matters on the exam 2 problem, the exam 1 problem, know that when you go look at runtimes for graphs, m is less than equal to n squared. But if a runtime for a algorithm can be done in O of n plus m, that's always going to be the runtime given and not O of n squared given. And that will be considered faster than all the other algorithms that runs in O of n squared. It is a standard for how algorithm runtimes work. So if you don't believe the TAs, just go in and search for runtimes for graphs, and this should make it very clear that we use the tightest bounds for runtimes to determine what algorithm is faster, not just because m is less than equal to n squared, so all n squared runtimes are okay. That's just not how things work. Any other questions, Mahmoud?
Yeah, just because I want to make sure I understand. In your situation here, you're saying we denote the array as T with n vertices. This T is the order array that pops out of the topo sort.
Yeah. Oh yeah, we can actually remove that.
And then
really
it's effectively we're just saying for each order we check if there's an edge between order of I and order of I plus 1, and if that is the case, then true, otherwise false, which is what you were saying originally in the prior solution, right?
Yeah, but I like this format better. It's just more narrative, doesn't get into like the deep weeds of it because we don't need it. I sorry. A lot of these solutions are written by me as a student, and I update them as I go as a TA that goes, oh, this is actually not the optimal way to write this, and this is how TAs want to read it. So that one just hasn't been updated, but I think this is a much better way to write it.
Okay, thank you.
Yep. That was 3.24, right? Yep. All right, I'm going to answer one more question, and then we're going to take a break, and then we're going to move on to shortest paths. I'm actually going to skip you, Manjunatha. I'm sorry. I've answered some of your questions already, so I'm seeing a new name, so I want to give another student a shot. Yanru? Yanru, you are muted if you are asking your question. All right, you missed your chance. Manjunatha, your question?
Thanks. Sorry, this is a basic question in my opinion. So if I take that example that you've shown here, right, and if I run the topo, there is a direct edge and there is a direct path. The DFS can explore the direct edge, and then the DAG would look like skipping the edges. So does it really work for those kind of situations?
Sorry, I'm not getting that question. I wouldn't run DFS after I run the top of sort, if that's what you're asking.
And
I don't
the
think that
topo
works.
sort itself, when you run here, so there are
Mhm.
like 1, 2, 3, 4. There are, there is a direct edge between the second node and the fourth node, and the topo that is using the DFS underneath can explore that direct edge rather than path. And then if that is the case, and we look at the source to sink topo sorting, then it would look like your original diagram over there, where it was
It'll still
skipping
give
the
you the right.
edges.
It'll give you the right topple sort, because what'll happen is that if you skip an edge, that vertex will end its traversal before the one that is skipped, and therefore the one before it skipped will get its post number afterwards. And so when you sort it from the post number from greatest to lowest, it'll still be sorted before it. So in this case, right, if for whatever reason it was to and I did this last week when I did the DFS, and I showed like, you go, okay, well, if I take a different path, what happens? The topple sort will work. If it was to jump this vertex and come here, this vertex finishes its DFS its explore run before this next edge that comes here, and so this will get a higher post number. If it goes this way, like if it doesn't take that skip, it'll go this way, and then this will get its post number, this will get its post number, this will get its post number, and then this will get its post number. So no matter what happens, no matter which edge it takes, this vertex will get its post number after this vertex, and therefore it'll be sorted as a before it. So it'll work.
Okay, thanks. Yeah, I was trying to work it out.
Yep. Okay. We are going to take about a 3-minute break, and then we'll come back and we'll start the shortest path problems. Yeah. I'm gonna give a couple of minutes. Actually, I'm gonna get water. All right. All right, I am back. So I'm not a big fan of people. I think it happens on Reddit a lot. People saying, well, you're going to a top 10 CS school. I think it's kind of gatekeepy when people say that. But what is pretty cool is that we are now a top 10 football team, and I think that's something you should brag about to your friends and families. Because man, it's been a long time since we've been ranked this high, and it's been amazing to watch. So that's pretty cool. Oh. All right, let's see what the next problem is. 4.1, I think, is running dice stress, which I will likely skip. That is in fact what it is. Yeah, we're gonna skip that one. 4.2 is running Bellman 4. I'll let you guys do that. 4.3.
Hey, Joves, before we start, can I ask a quick question not related to this section?
Sure.
So, last time for exam 1, you ran a tips and structure overview. Are you going to do that for exam 2 still, or?
Tips and what do you mean?
So last time for exam 1, you ran through like DP and DNC problem strategy and all those again, and also the structure and maybe the point allocation at high level, like for 20-point question, we have 12 points for this and 4 plus 4 for that. Are you going to do similar things for exam 2?
Sure. I will go over that in a little bit.
Oh, okay.
I have information about that. Let me just double check if I have any slides on that.
Thank you.
Yep. And if not, I can just kind of wing it and talk about it. What does my exam2 prep say? Yeah, I think I generally go over the same things I talked about like previously. So that like when I went over the exam 1 prep, I was just basically going through all the strategies I had already covered in a previous office hour. I think given that there's so many problems, I kind of skipped that.
Yeah, that's fine. But like, do you have any exam structure information to share, or like point allocation? Like how many questions
Yeah.
are we?
Oh yeah. So I think it's a good question. As far as I know, and again this can change, but wait till Monday and the full exam will come. Full exam supposed to come out. I believe it's once again 2 written problems. Not once again. It's going to be 2 written problems, 20 points each. Both will be graph algorithms, and then followed by 20 points worth of multiple choice. And the point structure is very similar to Divide and Conquer. I believe it's 12 points for algorithms, 4 points for correctness, 4 points for runtime. Let me double check that. It should follow the same as your homework grading that you should have already received. So student, correct me if I'm wrong. We do change it every now and then, but I don't think that one has changed in a long time. But we'll just double check. Let's see, homework 5. What's the rubric look like? Yeah, 12 points for algorithm, 4 points for correctness, 4 points for runtime. You have 2 written problems and then multiple choice, and it'll be 20 points each.
Okay, thank you. Yeah, so that's great information. So and for exam prep, would you still say the assigned practice problems and homework way more important than the additional problems, especially for those with marked as hard or whatever, they are less relevant?
Yeah, it's the exact same thing. I would say that your homework problems that were assigned are super important. The practice problems that have model solutions are probably the next level of importance, and then the problems that we're going through today, still important if you want to get a full picture, but probably not as important. And then the questions that are marked as hard are questions I probably won't even answer. It's kind of up to you to decide if you want to approach those or not. I think I approach all of them to get a solution, but it's at such a like high level in terms of like difficulty. I don't think it's like good value for students to use it as preparation unless you've already like conquered all the other problems.
Thank you.
For homework 7 and 8, if we don't have time to write the code part, can we just write down the writing steps like
Yeah.
the algorithm, practice,
Yep.
justification, and the runtime? But
Sure.
where can we find the right solution to the runtime, the final runtime? We want to just
So we won't grade those, unfortunately.
Uh-huh.
But what you can do is you can post it in the homework threads, and other students can sort of help guide you if they've worked on the homework. I really want
Okay.
to emphasize that like you should trust your peers. Like you should be discussing practice problems, homework problems. There's a lot of really, really good students out there that are, love to help other students and they would love to help, like, give you a different perspective on it. So if you just post in those threads, a lot of students activity can start. And even if you don't know the answer, go participate in those threads because, you could make an assumption that could give some other student an aha moment and then you guys can work together to come up with a solution.
Okay, thank you.
Yep, no problem. All right. Question. This is 4. Which one is this? 4.3. Yeah. All right. Squares. Design and analyze an algorithm that takes as input an undirected graph G and determines whether G contains a simple cycle, that is a cycle which doesn't intersect itself, of length 4. Its running time should be at most O of V cubed. Okay. You must assume that the input graph, you may assume that the input graph is represented either in adjacency matrix or with adjacency list, whichever makes your algorithm simpler. So there's a big clue that's given to you here is that the runtime should be O of n cubed. The other nice little hint that it tells you is that you can do an adjacency matrix. So what we're looking for is any sort of cycle that looks kind of like this. Right, that's a square. So there's A, B, C, D, and then there could be like other vertices here, and then so forth and so forth. But it doesn't want to concern itself with like the cycle of like something that goes over the same vertex twice. It just wants it like this little like square here. Okay. And the key thing to see is that in order for this square to appear, you're looking for two vertices. Such that they share two neighbors. Okay, so A and D shares two neighbors, C and B. That creates a square. The other way to look at it is that C and B shares two neighbors, A and D. That creates a square. So anytime that happens, you have a square. Now, it is efficient, I guess, to look for this when you have an adjacency matrix. So we can either start with an adjacency matrix, which I suggest you do, or you can create the adjacency matrix. Now, the other thing that you should know is that we typically want you to work with an adjacency list, and we typically assume that your input and output are adjacency list. You can specify using an adjacency matrix if you want to, but our inputs are adjacency list. So the second you use an adjacency matrix, your runtime is now O of n squared. Okay, so keep that in mind because it takes O of n squared to create an adjacency matrix. Okay, so we're going to be assuming that we are given an adjacency matrix. If not, then you just say I create an adjacency matrix out of the adjacency list that takes O of n squared. And we're going to do exactly what I said. We're going to, for all pairs of vertices U and V, check the row, right? So you can check the row that they're both in and see if they share at least two neighbors. So you have your A here, and then you have your all these things, right? And then you have your B, and then you have all these other vertices. And so what you're looking for, and this takes O of n, is that you just want to know if this and this are the same, this and this is the same, or this or this or this, and you need two of them. Okay, once you have two of them, you've created a square. Okay, you don't want to check one and then check the other. You don't want to check them, in weird orders. Just pick any two any pair of vertices and linearly scan their adjacency matrix row to see if they share the same the same neighbor. Don't scan one and then for each one up top scan the bottom, right? Okay, that's not efficient. You want to just scan these together. So if any such pair of vertices exists, then return true. If not, return false. Okay. So this question is basically asking if two vertices share two neighbors, because if they do, then four vertices would form a square. So by using an adjacency matrix, we can do this by scanning two rows at a time for all pairs of vertices. Now, what's the runtime? Well, there's n squared pairs, right? And it takes all of n to scan that row for both of them at the same time, and to compare the two rows. And so it's all of n cubed for your runtime. All right. Questions. The cache.
Hey, I noticed that we're not using any black box algorithm here. And from my understanding,
Yeah.
using a black box is mandatory.
Yeah. So we wouldn't give you this problem that doesn't require a black box. This is just sort of an exercise for understanding how the relationship works.
Okay. And I was doing a solution which uses basically Floyd Marshall and could get the solution, I guess.
Floyd Marshall. What's the runtime Floyd Marshall? It's O of
It's O in cube. It's O in cube.
O in cube. Yeah. So yeah, you could use Floyd Marshall and then check its output to do the same thing, do the same scan, right? Because you'll have infinite distance to any vertex you can't reach, and then if you scan that table and for any term, yeah, you know what? Next time I do this, I will use Floyd Marshall because that would be using a black box. That's fine.
Yeah, basically, check for all pairs where distance is 2 and then check if they have the same neighbors. Okay.
Yep. That works exactly fine. All right. Nicholas?
Would we also need to check that the pair U and V do not have a line or an edge connecting themselves? Because then it wouldn't be a simple, we would get back to the triangles we were talking about.
I mean, you would, it's allowed. You just don't use that. You just don't use that line as part of your cycle. Like a cycle can isolate the edges that create the cycle. It doesn't matter if you have
I
an
wasn't
edge there or not.
sure with the simple cycle if it could be smaller too.
Yeah, the simple cycle part is just like a silly thing that they put in there. It's not needed. It's like saying that we have a simple graph. Like you assume it's a simple graph unless told otherwise. So you don't really need to say it. So like a simple cycle is what's assumed to be what it is. Yeah, you're fine. All right. Charisma.
Hi, yeah, so if we were to use an adjacency list for this one, could we, would we be saying that you're going to be going through the adjacency list and then for every UV VU pair, you see if there is an outgoing edge that it has another outgoing edge, so you have to follow it down a BFS of hops 2 between these two pairs?
I'm sure you could write it up in some way. Again, I want to try to write up 5 solutions for each of these problems, but I'm sure there's a way to do it with just C list. That's fine.
Okay.
Yep. Spencer.
Oh, I was gonna ask a potential other way to solve it, but we can go on.
Okay, thank you. Appreciate that. All right. Next problem. 4.8. Professor Flake. What's this problem? Okay. I like this problem because a lot of students will get shot by this. And I think it's important concept to understand. Do not try to run distress on negative edges by shifting the weights. It does not work. It cannot work. And we'll show you why. Okay, so the claim is that the shortest path from node S to T in a directed graph with some negative edges add a large constraint or constant to each edge weight so that the weights now become positive. then run Dijkstra's algorithm starting from S, and then return shortest path. Is this a valid method? Why or not? So here I've drawn our an example where we have 1, 2, 3, 4. I probably should have named it A, B, C, D, but whatever. So our shortest path from 1 to 4 is through these negative weight edges, right? So it's -1, -1, -1. So this path right here gives us -3. Okay, so that's our shortest path. But if we were to shift all of it, because we shift each edge independently from the others, it disproportionately affects paths with a lot of edges, whereas paths with fewer edges get shifted less. Okay, and because of that, if we were to say add 3 to every edge, this path is now equal to 6. Okay, whereas this path, which used to equal to -2, is now equal to 1. And you're gonna say that the path from 1 to 4 is the shortest path when it's really not. Okay. Any questions on 4.8? Good. This shows up on the exam. Every single person who has attended this office hours is going to get this right. All right, let's see. Next one is 4.11. That's 4.11. Shortest directed cycle. Okay. Given algorithm that takes as input a directed graph with positive edge lengths and returns the length of the shortest cycle in the graph. If the graph is acidic, it should say so. Your algorithm should take time at most of n cubed. Okay. So we are going to see, and I will say that we're going to use full Warshall, and there are different implementations of what Floyd Warshall does with this diagonal. Some will say that it is initialized to 0 because the shortest path for a vertex to itself will be 0. Some will say that it's initialized to negative infinity, positive infinity, and then the number ends up being the cycle to itself. I'm going to give you a solution which it doesn't matter what the diagonal is set to because different implementations says differently. If you were given this problem, I would expect you to use the implementation that is shown in the book or in the lectures or as stated in the black box post. Okay, so that is the implementation you would use to try to solve this problem. I'm just going to ignore all that and give a solution that doesn't care about the diagonal. Same runtime, but because I don't want to have to try to remember what that diagonal represents, I'm just going to avoid it altogether. So if someone asks me, why didn't you just use the diagonal? I'm just going to ignore you because I already explained why. All right. Then we're going to run the Floyd-Warshall algorithm, and then we're going to get a distance. Okay. So then we're going to do for all pairs of vertices, we're going to check the distance from U to V and the distance from V to U, and return the smallest sum of those edges or those pairs of vertices. If the smallest sum is infinite, then the graph is acidic. Okay, so Floyd-Warshall gets us the shortest path for all pairs of vertices. Since the graph is directed, a shortest cycle between any two vertices is the shortest path from U to V and then from V to U, right? So we have a path from U to V, then a path from V to U, and that creates our cycle, right? And because we're looking for the shortest path, our shortest cycle is going to be some combination of those two paths. So the shortest cycle in G must be between two vertices. So checking all pairs of vertices, we'll find the shortest cycle in G. If for every pair U can reach V, but V cannot reach U or vice versa, then you don't have any cycles. And if you don't have any cycles, then the graph is acidic. And if it's acidic, you want to say that it is. Okay. Floyd Washoe is all been cubed. Checking distance between all pairs all been squared, and therefore it's dominated by the Floyd Washoe algorithm, all been cubed. Okay. Any questions regarding this solution other than why didn't I use the diagonal? Go. Good. Okay. I also think it's easier to understand it this way than trying to like argue out what the diagonal is trying to do. Yeah. Mahmoud?
Yeah, I've seen this implementation a couple of times where you find the shortest path. It's usually the distance of u v plus v to u. And I don't know why my brain just does not want to understand why this produces the shortest path. I'm struggling to understand
Shortest cycle. Okay. So.
Yeah, shortest cycle, sorry.
Yeah. Suppose I have a vertex A and a vertex B. Okay. And then I have some path, blah, 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 blah. Okay. So this is my shortest path going from A to B, right? And a cycle is basically going from one vertex to another and then back again. Okay, so that in a directed graph, that's what a cycle is. Okay, it's a little bit it's different for an undirected graph, but we know this is a directed graph. So now that we have this path, we're looking for a path that goes all the way back to A. Okay, and there can be a lot of edges and a lot of vertices between these two, what have you. But this is my cycle, right? The distance of the cycle would be the distance of this distance plus this distance. Okay, that is the distance of my cycle. This entire circle has the same distance as the top of this not really circle, oval, the top of this oval and the bottom of this oval. Now Floyd Washoe is going to try to minimize this path. Okay, Floyd Washoe is always also going to try to minimize this path. Okay, so when this path is minimized and this path is minimized, the sum of the two is also minimized. And the sum of the two gives us our distance for the cycle. And our smallest cycle within our graph is the smallest sum of some pair of vertices of their shortest paths. And that's why we do this. Does that make sense? Hopefully.
Yeah, that seeing it drawn out makes it make more sense. Thank you.
Great. Yeah. All graph problems, when in doubt, just draw it out. It's meant to be a very visual topic. So if you're not sure about something, just start drawing, and it might just be like, oh yeah, that now looks right, and that makes sense. Right.
Yeah, it just also
Anika?
helps that you're explaining it to me. So,
Okay.
thank you.
Yep, no problem. Anika?
Yeah, quick question. So anytime you have a graph that has edge weights and it says shortest cycle, like it always means shortest sum of the lengths, right? It's never going to ask for shortest number of edges. Because like when I first read this, I was like, oh, okay, it's like one vertex to another that has anti-parallel edges, but that's not what they're asking, right? They're asking about the sum of those weights.
Yeah, I mean, if you have weighted graph and you're asked for distance, length, sum of the weights, whatever, it means the sum of the numbers that you're given. If you're given an unweighted graph and you're asked for shortest distance or whatever, then it's a BFS check of the number of edges from one to the other.
Okay, and with the
And
weighted
anytime
graph, we don't ever consider, like, is there any algorithm that could tell us more for like number of edges?
Yeah, if it's a weighted graph, you can still run BFS on it. BFS would just ignore the edges. Yeah, it would just ignore the weights and give you the least number of edges between vertices.
Okay, cool. Thank you.
Lennon?
So I did kind of the same solution, but instead of iterating over pairs of vertices, I iterate over the edge set. And for every edge UV, I look at the minimum of the weight of that edge plus the distance from V to U. I think that achieves the same ends, right? Because the edge is directed, so the path V to U won't go back through that edge. It'll go through another path.
I'm not quite sure I understand your approach, but I also don't really want to because I'm going to try to focus on my solution to these problems. I'm sorry. I really need to get through these problems with the people. So
Yeah, no, that's
that.
okay.
Sorry. Okay. All right. All right. Let's move on to the next question. We are on 4.12. Which is shortest undirected cycle rate. We have an O(n) squared algorithm for the following task. An undirected graph VE, edges length E greater than 0, so positive edge weight, which means we don't have to worry about Dijkstra's. We don't have to worry about Bellman Ford or Floyd-Warshall. We just have positive edges. And a single edge E. The length of the shortest cycle containing edge E. Okay. Now, I just told you that we could do this with Floyd-Warshall earlier. But we are looking for OV squared algorithm, and these are positive edge lengths, right? So one way to do this using Floyd-Warshall, which we just learned, was if we wanted a cycle that contained edge E, right? If E was equal to UV. This is not the right answer, but we will talk about it. E is equal to UV, right? So the cycle that contains UV would be a path that includes a U to V without the edge UV, right? So if I was to run, if I remove the edge UV and I run Floyd-Warshall, that gets me my path, my cycles, and then I could just add this back in. We can do all that, but we could do this much easier with Dijkstra. So what we want to do is we want to say, okay, well, we have a cycle, if it exists, that's UV, right? And then I think we already did a problem that's very similar to this. Did we not do a problem that's similar to this? What problem did we do that was like, did I already do this problem? Why am I getting this like hit of deja vu all of a sudden? What was my list of problems today? Oh, it was to find a cycle. Okay.
I think 311 is similar.
Okay. Right. Okay. So we have UV. And then we have this path, right? So in order to find the shortest cycle, what we're saying is that, okay, well, UV has to be included in my cycle. And so that's already clear. We can include the edge weight of that. But if we were to remove this, the shortest cycle that includes UV is now the shortest path from U to V without this edge. If I can find a really short path from U to V, that's my shortest path. And then I will add, because no matter which cycle I find, I have to add the edge weight of this edge. I'll add it to my shortest path, and therefore that's my shortest cycle, including UV. Now this problem is kind of lame because it tells you OV squared. That's actually not the optimal runtime, but we're going to make use of it just because it asks for it. So I'll give you the answer, and then we'll talk about it. All right, so we're going to make use of Dijkstra's because we don't need because we know exactly the edge that we want to work with, and we don't have negative edge weights, so we can use Dijkstra's. Okay, so we're going to remove the edge. We're going to run Dijkstra's, and then we're going to return the distance of U to V. So we run Dijkstra's from U because we give it a source vertex, and we're going to return the distance from U to V plus the edge that we removed. Okay, and that's it. That's the answer. Okay, so because we have to include our edge in our cycle, the way to minimize the rest of the cycle is to find the shortest path that completes it. So removing it gives us the opportunity to do that. We run Dijkstra's to get the shortest path from U to V, and then we add that edge back, which gives us the shortest cycle with UV. Now the runtime is O of M to remove the edge. You can also say O of N. That's fine too. Running Dijkstra's is O of N plus M log N, and that's your overall runtime. Now, while we normally use the binary heap version of Dijkstra's in this case, and we would accept this as the runtime, this is fine. If we wanted to bound our solution to the problem statement of O of n squared, there's a different version of Dijkstra's using the array as its data structure. So I think there's a heap version, array version, and then there's like a Fibonacci heap version. They all have different runtimes, serve different purposes. Generally, we just use the binary heap version and say it's O of n plus n log n. In this case, we're going to give it the O of n squared runtime because the question asked for it. And so the overall runtime running Dijkstra's is O of n squared and X is O of n squared. But we wouldn't phrase the question like this. First of all, we almost typically never give you the target runtime. And second of all, if we did give you a target runtime, it would not be O of n squared. Okay. So that is the solution to this problem. The catch?
I want to go back to the previous problem only because I think just like this one, using Dijkstra on the other one should give us a lower runtime. We could just run Dijkstra's for all the nodes and then get the distance u to v, v to u. That would give us, I guess, n into n plus m into log n.
So you're saying this one, if we take O of n and we times it by Dijkstra's runtime, which is
Yeah.
log n, that, right?
Yes, that should be slower than that should be faster than n cube, right? Like
so this is O. This becomes O of n squared plus O of n m times I mean, it's arguable. It's arguable because this runtime right here, this O of nm times O of log n, could potentially be worse than O of n cubed. It could be potentially be better than O of n cubed. But I think if this problem was given the way it was, I don't know. I would need one of the graders, head graders, to let me know which one they would grade as faster.
Well,
I think
because
if the target
it didn't say it's sparse or dense, right? So we can either could be possible when it's dense, wouldn't n be just like n squared? Then it would be n cube log n, so it would be worse in a dense scenario.
but we don't make that assumption, right? That's why we call it linear for all
Right,
the
but
graph
like,
problems. Yeah.
so what you can say though is that if the graph is very dense, this is a worse runtime. Oops, this is a worse runtime. If the graph is very sparse, this could be potentially a faster runtime. Because m is going to, like, if m is equal to less than n,
Right, but generally we consider n plus m as linear, right? Because we don't make that assumption of.
this is not O of n plus m though, because you're multiplying the n across it, right? So this is actually going to be O of n times this n, which is O of n squared, and then O of n times m log n, which is O of nm times O of log n. So this right here, this multiplication is what's going to tie us up. We don't know if this is better than O of n cubed. We also don't know if it's worse. So I would say that if you were to give this solution, I don't know what the graders will do. But it is definitely not just O of n plus m. Like this multiplies out to be this right here.
Right.
And this
right.
this has a potential to be worse than O of n cubed. Oh wait, did I do this runtime wrong? Yeah, I think I actually did the runtime wrong. Sorry, let me take this back. Student pointed out, good point, that it's actually this runtime. So you multiply this out, you get O of n squared plus n m plus, no, times
Log n.
no. So this right here. So this term right here could potentially be O of n cubed. Yeah. Yeah, can't really tell. So couldn't argue that it was faster or slower. Wouldn't even know if it would be appropriate or not in terms of runtimes.
Okay.
I don't like this answer though, I'll tell you that. I hate answers where it runs an algorithm from every vertex. So
Yeah, my only concern here is we have been told again and again, which I completely agree with, is don't assume m is equal to n square. Consider m is equal to m for all the previous runtimes filed.
No. We definitely do not say that either. We do not. We tell you to don't assume anything about n or m. You don't know what their relationship to
Right,
each other is. So we don't assume m is equal to n squared. We certainly don't assume m is equal to
right,
n either. Which is why I'm
right.
saying that I don't know if the runtime is faster or slower. Yeah.
Okay.
So yeah, I can't argue if this is faster or slower. I just don't like the answer. That's all I can really say. All right. I'm gonna answer one question to move on. Mahmoud?
Yeah, sorry, there was a question in the chat, and I don't know if how to explain it. But in the question we just did, which is finding the shortest cycle containing E, you said
Yeah.
that removing the edge was
Yeah.
O of M, but shouldn't that just be O of 1 because you're removing a singular edge?
It's either O of M or O of N. It is not going to be O of 1. The reason why is that you have an adjacency list. So you have some A, and then it points to B, C, D. And it doesn't actually have to be alphabetical, right? It could be like I, H, D, or whatever. So you start with your first endpoint, and then in order to find the edge you want to remove, you have to go, is it B? No, C, D, I, H, E. So you go down the list. Now this right here is going to be upper bounded by N or upper bounded by M, right? Because you can only have so many edges, and only so many edges can be applied to A. So all of N, all of M, both would be fine. Typically, when we give a problem like that, it's not going to be the thing that determines your overall runtime. I just like to say O of M whenever I deal with edges, and O of N whenever I deal with vertices. But if you wanted to say this was O of N, you could as well. But O of 1 is definitely not okay.
Yeah, I thought it was like we know where E is, so we can just remove it from the list. I was not aware that we had to like loop over it. Thank you.
Now, I will say, off record, so don't use this in your problem. Most of the time, a adjacency list in like actual coding is done with hash sets or hash maps, and typically in the real world situation, we can you consider it to be O1, but because of the way we teach this class as worst case runtimes, a hash set or hash map would also be O of n, so it doesn't really matter. I have fought to try to teach it as O1 using hashes. I have been outvoted by all the other TAs, so we cannot do that. So therefore, you have to consider it as an adjacency linked list.
Okay, thank you.
Yep. All right. Let's go to the next problem. So that was 4.12. 4.13 is it cities and highways? Three. Okay. Students claim this. Someone claims I am the bad boy of the TAs. We actually at one point it was really funny. I made an alignment chart for the hit TAs. I basically made a like which TAs are chaotic good or whatever. And I think we mostly agreed that I sit on about the chaotic good side. I tend to be for the students on the alignment chart when we were argue like points and how we want to give content to the students. And I don't always want to follow the rules just because they're there. So I tend to be on the chaotic good side, if that helps. All right. So you are given a set of cities along with pattern of highways, which is, by the way, why my office hours can run to like 4 or 5 hours, because otherwise it would just be 1 hour and I'll be done. But I don't. So you're given a set of cities along with a pattern of highways between them in the form of an undirected graph. G equals VE. Okay, so these highways are bidirectional, they're undirected, right? So each stretch of highway E connects 2 of the cities, and you know its length in miles, L. You want to get from city S to city T. There's one problem: your car can only hold enough gas to cover big L miles. There are gas stations at each city, but not between cities. Therefore, you can only take a route if every one of its edges has length less than L. So part A says give the limitation of your car's. Given the limitation of your car's fuel tank capacity, show how to determine in linear time whether there is a feasible route from S to T. Okay, so this problem is hopefully pretty simple, but it can like make you feel uncomfortable when you go to solve a problem like this for the first time, because you kind of want to just make a change. You kind of just want to be like, well, I just tell my algorithm not to travel down the roads that I can't, but you're not allowed to do that, right? So what you actually want to do is mess with your inputs, or not mess with your inputs, but update your inputs before you run your algorithm. So what we're going to do is like, well, if I can't travel over any road that has that's too long, then I'm just going to avoid them altogether by not even considering them. So what we're going to do is that we're going to create an alternative graph that says, okay, for all edges that is greater than the capacity that I have, just remove them from my graph. I don't even want to consider them. Now I run BFS with those edges removed, and I just check to see if T is reachable. So if S can reach T with those edges removed, then that means I can reach it, right? And notice how here is an example of running BFS on a weighted graph, because I don't care about my shortest path. I care about whether I can reach from S to T. If I had run Dijkstra's, this would be a slower runtime, right? And I do have edge weights, so it would seemingly make sense to run Dijkstra's, but I don't actually care about my distance. I just care about avoiding those roads that I can't take. And I've already removed them, so BFS doesn't have to worry about what those edge weights are. It doesn't even read them. It just checks to see if S can reach T, and that's it. So our correctness is that we remove these edges that we cannot travel, and once they're removed, all remaining edges are allowed by our tank capacity, and then we just see if they can be reached. Now, I've said that Dijkstra's can do the same thing. Dijkstra's can also tell you if S can reach T, but it's slower. You should only use it if Dijkstra's is something you're already running. Otherwise, BFS is the faster algorithm to check for connectivity. Okay. Any questions on part A?
Maybe I'm reading this wrong, but create a graph where all the edges E exist such that LE is greater than L. Shouldn't that be less than or equal to L in step 1?
So the way to read this, and I should probably edit this. This is G without E, and E star is all the edges that's greater than L, and so G without it would be all the edges that are less than or equal to L.
Oh, okay, thank you.
You know what? Let's retype it. That is kind of confusing. create G prime by And by the way, this is why one of my tips for doing well in this class is to work in a study group and teaching others, even if you're really good at the topic. Like to me, that read perfectly fine, and I perfectly understood what I wrote for myself. But if a student gets confused, I will look at it and go, yeah, you know what? That is actually pretty confusing to read, and there's a better way to say it. And if there's a better way to say it to another student or someone I'm trying to teach the solution to, it's a better way to say it on an exam. So if I was to write on the exam, I don't want to confuse my TAs, just like, I don't want to confuse another student. I probably just rewrite this. So create a G prime by removing from G all edges that have a length greater than L. Does that make more sense? Hopefully.
Yeah, that makes more sense. Thank you.
Great. Okay, so now we run the BFS. We're going, oh, snap. I actually made a mistake. You show these same solutions to like thousands upon thousands of students, and you still catch mistakes like this at some point. All right, so we run the BFS algorithm on G prime, on the updated graph. Okay. All right. Let's see, more questions. Ricardo?
Can you hear me?
Yes.
Okay. I just had two very quick questions related to this. They
Okay.
might also be similar to previous questions and previous problems. But I was wondering, in this problem, instead of creating a new graph by removing the edges, could we just run BFS on the original graph and simply ignore like these edges?
That
And
would
the other
be
question is
modifying the
also,
black box, and you would lose points. You would be
okay.
modifying the black box at that point.
Okay, and my other question is also here, since this is just like kind of like a reachability problem, could we have used DFS instead of BFS?
You can always do that if you want. I've answered that
Okay.
question multiple times. I'm not like trying to call you out, but you can always do DFS if you want to go the extra steps of like calling out CC nums and all that stuff. I prefer BFS because it's simple. It's something that's provided. But if you want to do DFS, you can. I just prefer BFS with this case.
Okay. Yeah, I was just wondering for this specific case, but yeah, also wondering for previous like. Thanks.
Yep. All right. Eduardo?
Yeah, I guess I'm a little confused about how this problem is framed. So they're saying that there are gas stations in each city, but not between cities. I guess that's a little confusing to me. I wouldn't know. So like, how do we know what edges to remove in this case? Like I did just not like which
So every
cities has
single
gas
edge
stations,
is
all of them.
every single edge is every single edge is a highway. Every single vertex is a
Yep.
city. So there is a
Right.
you can get gas whenever you reach a vertex. You cannot get gas in the middle of an edge.
Oh,
Therefore,
I see. I
yeah.
see. Got it.
Yep.
Yeah, thanks.
Yep. Moving on to part B. So part B is saying you're now planning to buy a new car and you want to know the minimum fuel tank capacity that is needed to travel from S to T. Give a Dijkstra's runtime algorithm to determine this. Now, you could use Dijkstra's with modifications, and that's probably what the book has in mind. But because our class does not allow you to modify black boxes, we're going to use a slightly, well, not slightly, we're going to use a different approach. Now, it's very Dijkstra's related. We're actually going to use one of the MST algorithms. So it turns out that when you want to find the minimum fuel tank to travel from S to T, you're looking for a path from S to T that uses the shortest roads. Because if you if S to T, right, Like if there was a direct edge from S to T that is like 100 miles, right? Your tank capacity would have to handle 800 miles worth of gas, right? But if S to T has, you know, a path to A, path to B, path to C, and here, right? And each of these, or, you know, 99, right? This is a much longer journey, but you only need enough tank capacity to go from city to city. So going from S to A to B to C to T needs a tank capacity of 99, right? It's smaller than the tank capacity of 100, even though you're going much further. And this is what an MST is designed for. MST is looking for a series of edges that uses the minimum weight needed, to connect your graph. So what we really care about here is an MST, and then checking for on that MST a path from S to T. Okay, so here's the solution to part B. All right. All right, so we're going to take our graph, and we're going to run Kruskal's on it to get an MST. Okay, then we're going to run BFS on M and S, and then we're going to use the previous check, the path from S to T, and return the longest edge, right? So your longest edge, right, is the capacity that you need, right? Because, oh boy. Lock, where's my lock? Right. So if this was 99, right, and this was 80, and this was 75, right? So still same thing. You still want to take that route from S to T because you can use a lower capacity than the 100, but your capacity is lower bounded by your longest highway, right? You could get from S to A using 80, but you need to get 99 to go from A to B, and then from B to C you only need 75, and C to T. I didn't put a number there, but you get the picture. So 99 is what your answer is, your capacity, right? So because we're using because we run this, we now we use the previous array from S to T, right? Because we know that why do I run from S to T? Oh, good, because we run BFS. That gives us the path from S to T, and we know that exists because we're running an MST. And so getting the previous will give us the shortest road, or the longest road we need now. So we create an MST, which is guaranteed to connect all nodes using the minimum edges. Since our tank capacity is limited to the maximum edge, we must take to get from S to T, going over the minimum edges. We'll minimize our tank capacity. We then run BFS from S over the MST, which can only have one valid path since it's an MST. Remember, MSTs do not have cycles, so there's only one path from S to T. So we don't even have to worry about if it goes the wrong way. This valid path can then be traversed to find the maximum edge along that path. Okay, and that determines our tank capacity. So running for scores is all of n log n. BFS is all of n. The reason why it's all of n is because we know that we have n minus 1 edges because it's an MST. You could just leave it as n plus m if you want. I just chose to simplify to O of n. Traversing the previous to find the maximum edge is O of n, and so it's all upper bounded by the Kruskal's algorithm, which is O of m log n, which turns out to be faster than O of n plus m log n. But that doesn't really matter too much because I think yeah. Okay. So that's our solution. Any questions about this? Someone asked why I use BFS and not DFS. What is everybody's obsession with DFS? Why do you use DFS for connectivity? Like I know why I use BFS because I know it's easier. Why does every student want to use DFS? Is there something that's like in the lectures or in the book that says like you should use DFS for connectivity? I'm like curious why every student wants to use DFS.
I guess that's
I
the
think
first algorithm we learned. So
it also doesn't go into depth when we cover BFS. It just says you should know BFS. So there you go.
All right. That's fair. That's fair. Maybe we don't do a good enough job covering. Okay. No. Any questions about this particular problem other than why am I using BFS? I'm always going to use BFS in this situation. Mahmoud?
Yeah. Okay. So my question here is, you're saying that O of m log n is the runtime of crystals, and crystals is the one that dominates. This would be fine because it beats n plus m log n, and that's perfectly fine. We don't have to make it exactly n plus m log n.
We wouldn't typically give you a target runtime, and I know why the target runtime exists for this problem is because what the author of this book wants you to do is modify Dijkstra's. We don't want you to modify Dijkstra's, which is why we came up with this solution. I think in the original, when this problem was given as a practice problem with the model solution actually suggests to modify Dijkstra's. I actually came up with this solution on my own, and that's why I like to present this solution as a non-black box altering solution.
Sounds good.
Yep. The cache?
So I have a more general question. So this was a very interesting use of MHT to resolve this question at which I didn't think of. In general, so how do we know that this is an MHT problem in general?
To me, the reason I thought of MST is I realized, oh, it wants me to use Dijkstra's. But I don't actually need Dijkstra's because all I'm doing is finding out which roads I want to take that can lower my capacity. I don't actually care about the overall distance from S to T. I care about which roads are going to be the cheapest for me, or the least amount of gas for me to go over. And as I was writing out the solution to using the Dijkstra's, I was just like, okay, well, instead of looking for the shortest path, I'm just going to look at I'm just going to keep track of the maximum capacity needed for each path and then take the minimum of that. And as I was doing that, I realized to myself, well, this is just an MST. That's exactly what an MST is. And that's why I pivoted and started using a MST solution instead.
Thanks.
Hi, Tim. Welcome to my office hours. Thank you for joining. Tim is correct. I run these office hours not because I'm required to. I run them because I enjoy them. I ran them even before I was the only TA that did office hours. We actually used to run like 2 office hours with Rocco, a different hit TA. Yeah, there's not much that can stop me from doing these office hours, unless I just stop working as a TA. I think that'll happen when I stop doing these office hours. I'll probably just stop being a TA entirely. Ajmal?
So I guess in this example, the example you gave where it's 100 from S to T, Dijkstra's wouldn't work here because even though that's the shortest path, the SABC path, the edge is the maximum edge. That's the one we care about, and that's the length. So that's really Dijkstra's.
Yeah.
If you try to use black box Dijkstra's, it wouldn't work for us in this example, right?
So yeah, so if you were to look up this problem on the internet, the solution you'll probably find is to update the way Dijkstra makes it's to modify the greedy decision that that Dijkstra uses. So instead of always picking the minimal path, it'll pick the path with the minimal longest edge, and you keep track of that instead. So it wouldn't be straight Dijkstra. You would have to modify it, which not a good solution for this class.
Yeah, makes sense. That was tricky.
Yep. Yeah, it is a tricky one because I don't think like the clues given in this problem helps you based on the way this class is structured. Hemakar?
Yeah. Hi, Joes. Can you hear me?
Yes.
Yeah. Maybe this is a naive question, but with your example on the graph, when we run the MST, is MST supposed to find the path with minimum total weight, right? So in this case, wouldn't the 100 would show up directly in the MST output?
No, because it doesn't care about SNT. MSTs do not work with a source and target. MST looks at the entire graph and considers the lowest weighted edge for all over vertices. So if you take a look at this one, right? Let's say add that just for completion's sake. This 100 is the heaviest unique edge on oh sorry, this arrow shouldn't have been there. This is a the 100 is the heaviest unique edge on this cycle. And because of that, because of the cycle property, that 100 will not be used. Because that's what MST cares about. MST cares about using the lowest weighted edges to connect the graph.
Okay, thank you.
All right, we are done with that problem. Next problem is 4.20 and 4.21. Where's 4.20? There's a network of roads G connecting a set of vertices V. Each road in E has an associated length. Wait, is that not what I just did? Oh, no, okay. Sounds so similar to the previous problem. I'm confused. Okay. There's a proposal to add one new road to this network, and there's a list of E prime of pairs of cities between which the new road can be built. Okay. Each such potential road E prime has an associated length. As a designer for the Public Works Department, you are asked to determine the road E prime, whose addition to the existing network G would result in the maximum decrease in the driving distance between the two cities S and T in the network. Give an efficient algorithm for solving this problem. Okay. I'm going to go off track for a second. I recently watched a really interesting video by Veritasium, which was talking about how there was two ways from going from A to B with different traffics, different traffic pattern. And what ended up happening is that it turned out that by adding a bypass between A and B that they thought would improve traffic, it actually made the traffic worse in all ways possible. It's a fascinating video that I think, if you're kind of into like these kind of algorithm type problems and how they're being solved, go watch it. It's really cool. This just reminded me of it because I know this is distance, so it's actually a different, thing that's being asked. It just reminded me of that video, and I love that video. All right. All right. 4.2. Where's my solution? 4.2. Okay. I'm gonna post my solution and then we'll talk about it. Is the solution correct? Oh, okay. I was like, my solution talks about S and T, but I don't see S and T in this problem. And I got really confused, but it's like at the very end of the problem that's being asked. Okay, cool. Okay, so this is my solution, and I'll read it, and then we'll talk about it. Okay, so we have two cities, S and T, that we care about. We want to find a faster way to get from S to T by connecting two of the cities within our network. We might not need to, but so we're gonna run Dijkstra's from S so that we get the distance from S to all other cities. We're gonna run Dijkstra's from T to get the distance from T to all other cities. Now, I believe this graph is undirected. Yeah. Okay. And then so for each edge in our E prime, so our set of edges that we want to consider, we're going to set the cost. Okay, we're going to set this cost function or array from U to V as L of U to V, and then the distance from S to U and the distance from T to V. Okay. Return the UV with the minimum cost in our function or in array. Okay. If there exists a shortest path from S to T and G already, then it is trivial to determine that no road should be built by comparing the original minimum path from S to T with the new minimum path from S to T over UV, right? So this is just like I'm not sure if the question is going to ask if I should always return the road or if I don't need to return the road, but just in case, I'm just going to, add this in there to say it. Generally, when we give a problem on the exam, we would tell you whether we care or not that there may not be a road to ask. To add, but this, this question wasn't written by the class, so just in case it does care about that, I just put that in there. All right. So if a new edge U to V is to create a new shortest path, then it would be combined with the path of the shortest path from S to U, and then from V to T plus whatever that edge would be, right? So you go from S to the beginning of that edge, and then go from V to the end of that edge, and then determine that edge. So by using Dijkstra's on the S and T, we have found the shortest path from S to all vertices and from T to all vertices. It is then a matter of checking each edge to find the best road to build. The runtime are 2 runs of Dijkstra's. Calculate the cost, takes all E. Careful here, it is the size of E prime. We don't know whether E prime is bigger than E, right? So E is all the rows that already exist. We may not have that many rows. E prime is the list of all rows we might want to consider. So we don't know which list is bigger, so we have to account for that in our runtime. So then our runtime is 2 runs of Dijkstra's plus going through all the edges in E prime, and so our runtime is Dijkstra's plus that. Questions? Makar?
I think, sorry, it was from my earlier question. Sorry.
Okay, no problem. Someone in chat said that CGV Gray has a similar video. I also love CGV Gray. He is also a very great content creator. Mahmoud?
Hi, Joves. Sorry, I might be kind of stretching here, but wouldn't the length of E just be M, or why is that different?
The size of E?
E prime.
Yeah, so you are given a graph, right? That starts off over. Oh no. Okay. So you have O of n M, right? You have M edges, right? So if I told you I had a graph like this, right? Wait, what happened to my?
So we can't see anything.
I realized that I'm trying to. Oh, why did I try right up here? Oops. All right, let me. I think I had the wrong screen. All right. Right. All right. So if I had some list of vertices and I have, some edges like this. And this isn't like, this is kind of separate from. So I have 2 edges, right? My size here is O of 5 plus 2. I have 2 edges, right? Now, if I give you a bunch of candidate edges, let's say this one, 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 this one. So how many edges at once? 1, 2, 3, 4, 5, 6, 7, 8, right? So that's 8, right? There's no way, not based on the problem, to know whether you have more edges originally on the graph or more edges as candidate edges to add, right? So the two separate numbers you don't really know, so you just consider it in your runtime.
Understood. Okay, thank you.
Yep. So notice how here I use n and m because that's the preferred variables I like to use, but there's nothing that this is there's no variable that like automatically gets assigned to this, so I use the magnitude of E prime.
Okay. Cool. Thank you.
Okay. Yep. I'm going to cover 4.21. 4.21 is going to take a while, but I will. Okay. Now we are running up to about 3 hours since I started office hours. This 4.21 will conclude the suggested graph problems. I know there's a whole set of MST flow problems. Looking at it, my guess is it will probably take me about 2 hours to cover. I don't know if students want to stay around for 2 more hours after the initial 3 hours for a total 5-hour office hour. I could, or I can just do it tomorrow night. So I'll let you. I'll see how chat feels while I cover 4.21. But if you have an opinion, make it known, because otherwise you won't get your vote. All right. 4.21. Oh, this is such a massive problem. I'm not going to let students who aren't here vote just because they're going to watch a replay anyway. So it doesn't really matter how they watch the replay if it's going to be in 2 parts, right? Oh, there's a mix. I don't have a clear consensus. All right. Shortest path algorithms can be applied in currency trading. Okay, so first of all, this problem is actually pretty difficult, so don't feel too bad if you didn't quite get it. I will also say that this was actually my homework problem when I took the class, and it was really hard. And one of my people in my group, Asia, who as you know is a math major, was the one that actually helped me solve this, because without Asia, I don't think I would have been able to figure this one out. So shout out to Asia for helping me with this problem. But we'll go through it. And this is why I don't know if I said this to the class at the beginning of the semester. I always suggest that I have like an ideal study group that I suggest to students. One of which is to find a math major and try to get them into your group. It's less important now because we don't cover RSA and FFT as part of the class anymore. But having a math major when those 2 topics come up is like a lifesaver. And even when you don't have those topics, I think a math major just sees these problems a little bit differently, especially in how you have to write like a proof-esque type solution. And I think math majors are super helpful. You need them more than they need you, to be honest. All right. Let C1, C2, ... CN be various currencies. For instance, C1 might be dollar, C2 pound, C3 lyre. For any 2 currencies, CI and CJ, there is an exchange rate, RIJ. This means that you can purchase RIJ units of currency, CJ, in exchange for 1 unit of CI. These exchange rates satisfy the condition that RIJ times RJI is less than 1, so that if you start with a unit of currency C, change it into currency CJ, then convert back to the currency CI, you end up with less than 1 unit of currency. The difference is the cost of the transaction. Give an efficient algorithm for the following problem. Given a set of exchange rates RIJ and 2 currencies S and T, find the most advantageous sequence of currency exchanges for converting currency S into currency T. Toward this goal, you should represent the currencies and rates by a graph whose edge lengths are real numbers. Okay. So basically, you're looking for a way to find the shortest path. You want to pay, you want to pay the least bit of penalty as you go from some source currency to some target currency. And the numbers here are used for multiplying, so that doesn't really work with any of the algorithms that we have. So what do you do about that? Well, it turns out, and this is the thing that Asia taught me. I mean, I kind of knew about it once she told me, but you can do some tricky stuff with logarithms. Okay. This is something like, you either have, and be honest with yourself, you either have seen this problem before, or you're a math major, or you looked it up, because there was no way I was going to get the solution without HSL. help. All right. So what we need to do is we need to convert the multiplication of exchange rates into addition of weights. Okay, so we can achieve this by using logs, because log of x times y is equal to log of x plus log y. Why this works, I don't know. Asia will be able to tell you, but it's math. Math is magical. We create a graph G such that the vertices represent each currency and edges represent each exchange. So R of ij, we create an edge E equals ij. Now we need the weights, right? What do we assign to the weights? So for all R ij, we are going to assign this as the weight. So the weight of ij is equal to the negative log of Rij. Okay. The log of Rij changes our multiplication to a possible addition. We use negative because we want to invert that. We want to make it so that we are trying to lose as little as possible. So if we didn't put the negative in there, when you add things together, you're actually looking to get the smallest end result, but we actually want the largest end result, and therefore we invert them with negative. We run Bellman-Ford on this because we can't use Dijkstra's. We have negative edge weights here with a negative log, so we have to use Bellman-Ford. We get back a brief array, and then we can look up a sequence of vertices of the shortest path from S to I. This is how we do single source shortest path with negative numbers. We return the path from S to T. This works because Bellman-Ford algorithm gives us the shortest path from S to T, to any T. Shortest path gives the most advantageous sequence of currency exchanges for converting currency S into currency T. Note, if there's a negative cycle in the graph, so we don't really care about that right now. We're going to care about it in the next section. But if there's a negative cycle in the graph, this may not be the correct answer. But we're going to look for that in the next problem. Yeah. So we convert the runtime to convert Rij to Wij is all of M, right? There's M edge weights, so conversion would be all of M. And then running Bellman-Ford is all of M n times M, and of the runtime ends up being O and M. Now, here is the perfect example of why this runtime is considered optimal over Floyd-Warshall. Floyd-Warshall would have also worked, but Floyd-Warshall would have been O of n cubed, right? And we say that n squared is greater than m, and so you would argue from the exam, if you were that type of student, that O of n cubed equals O of n, and that's simply not true. We consider this to be the more optimal runtime. If you ask Google, ask anyone which one's the more optimal runtime between Bellman-Ford and Floyd-Warshall, you're going to get Bellman-Ford, because that's just the way that these runtimes are compared against each other. All right. Any questions about this particular solution? Equin?
Hi, I don't understand step one. Can you explain like why Wij equals negative log R again? Thank you.
Yeah. Yep. So first of all, we would not give you a problem like this, which requires you to have like some, some math aha moment for this. Actually, Dr. Brittle does not like giving problems that has like an aha type of solution. I have presented problems to Dr. Brittle, and Dr. Brittle has turned them down by saying this takes a aha moment. So we try to avoid this. This problem here requires an aha moment. I think it was okay to assign as a homework back when I was a student. We would probably not do this as a homework, and almost certainly not as an exam. So if you don't understand the math relationship between the two, it's okay. It wouldn't come up on an exam. And the reason why it works, this relationship, is that this log of x times y equals log of x plus j, log of x plus log of y is just a mathematical relationship that's true. And so this takes a multiplication problem that you're trying to, find some optimal way to to multiply the numbers into an optimal way to sum up the numbers. Okay. So that goes from that takes our so when this Rij, so the way you want to look at this is that if I was to go from I to J to K, right? My currency conversion is taking whatever X I have, we multiply R of Ij, right? Because that's our conversion rate. And then we multiply again by R of Jk, right? Okay. So that is the process for which we would get our equals to y some value, right? We multiply them. But because our shortest path algorithms works with addition, we don't want to multiply them. We want to convert them to addition. Now, the relationship between these two things multiplying under, and putting a log around it, like it's not the full equation. You don't get the end up number. You're just looking for a path that uses the relationship. So if we take the log of this, okay. We take this and we said, okay, well, the multiplication relationship, stays if we log it all. And if we log it all, then we can also just rip them out and then just do addition instead. And that gives us the ability to do shortest path. Now we change those into negatives because we also want to imply that we don't want the multiplication to get us the results of this relationship to give us the smallest number. We want the relationship of this to give us the biggest number, and therefore using negatives flips that. We want the bigger the number, the better, because we want to lose as little of our currency as possible through these transactions. Again, if you can't quite understand the relationship here, it's okay. I don't think that's too big of a deal. I just think it's okay, you're just taking a multiplication relationship and you're turning it into an addition relationship by using the fact that log of x times y is equal to log of x plus log of y. That's it.
So it's like you're kind of modeling this question and you kind of define the weight yourself instead of giving a graph with weight.
Yeah. Because all you care about is the path. You don't care about the actual end result. You just care about the pathing. Okay. All right. So part 2. Hold on. I actually have to go calm my dog down. I'll be right. Sorry, my dog is both friendly and protective. So if someone lingers at the door for too long, he'll just keep barking until they go away. And I have to go downstairs and tell him that it's okay. Otherwise, he'll just keep barking because he thinks he's protecting the house. All right. Question, Shanek?
Hey, hello, Joves. Quick one. I just wanted to get your thoughts on when it is okay to modify edge weights to make them negative or positive. I know you spoke about this once before, but if you can give a quick some thoughts, it would be great.
So you can't just die stress does not work with negative edge weights, right? So if you have negative edge weights, you want to consider something else, right? And so that's what I've done here. I've looked at this problem and I go, okay, well, I really need the negative edge weights because I need to maximize my end currency. I don't want it to find the smallest possible currency. I need to find the biggest, and therefore I need to use negatives. And so if I need to use the negatives, I'm going to use Bellman-Ford, and I'm okay with that. And for this particular problem, I needed to use Bellman-Ford, and that's okay. It's not that you can't have negative edge weights on the graph. It's just that certain algorithms don't work with it, and so you have to pick a different algorithm, and that's all that's done. Turning a graph from positive to negative isn't like inherently not okay. It's just, you know, if you get a graph like that, don't run die stress unless you have some way of working around it.
Gotcha. So quick comment here. So going back to one of the problems in that we saw earlier, where adding a constant offset to the negative weight would give you a wrong answer. If you were to
Right.
just make it like flip the sign, it wouldn't give you a correct answer either.
Right.
So
You would just not use die stress at all in that situation. That's the whole point of that question is to say, the question was, if I have negative edge weights and I do some shenanigans, can I use die stress? And the answer is no. Regardless of what shenanigans you do, you cannot go use you cannot use die stress. It's
okay,
not saying that the graph itself is illegal or there's something wrong with it or you don't want to solve that problem. You just can't solve that problem with die stress.
Thank you.
Yeah. All right. Cool. All right. Second part of this question asked, the exchange rates are updated frequently, reflecting demand and supply of the various currencies. Occasionally, the exchange rates satisfy the following property. There is a sequence of currencies, C1, C2, blah, 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 such that the rates are greater than 1. This means that by starting with a unit of currency CI and then successfully converting it to currencies CI2, CI3, blah, 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 and finally back to CI, you would end up with more than 1 unit of currency, CI. What? Such anomalies last only a fraction of a minute on the currency exchange. I don't know why it doesn't say seconds. What the heck is a fraction of a minute when it's just seconds? But they provide an opportunity for risk-free profits. Give an efficient algorithm for detecting the presence of such an anomaly. Use the graph representation you found above. Okay. My team actually works with currencies a lot, especially currency exchanges. And you almost, when you do like a currency exchange for pricing, you almost never actually go from one currency to a bunch of middle currencies. What you end up doing is you take the currency, you convert it to some universal currency. I think we call it a nuke. I don't know if that's like within my team or if it's external. You convert it to one currency and then you convert that currency to the final currency. So it's like a 2 hops exchange. We are not in the business of exchanging currency to make a profit. So maybe there is something into it, but in terms of like e-commerce or commerce of different currencies, that's all you do. And those get updated like not like instantly, super frequently. Like this sort of like, you know, trying to make money exchanging currencies, I don't think really works in the real world. Not that I've seen. All right. So this is part B. Okay. So the anomaly can be reduced to see if there's a negative cycle exists. Okay, so basically, because we have flipped our signage, right? We've made it so that the shortest route is the optimal currency exchange route to keep the penalties low. Okay. In that sense, if you can, so the way we design our our initial set of the graph is that rather than maximize our end result, what we're really doing is minimizing penalty. If you minimize the penalty forever, eventually you get a positive, like if every exchange I'm trying to lower my penalty and it goes upside down, I end up making a profit, is basically what this question is asking. So I'm looking for a negative cycle within my graph. So negative cycles can be found using Floyd-Warshall. Because Bellman Ford is a single source, we're looking for a negative cycle on all currency pairs. And so we need Floyd-Warshall to get all sources shortest path. So we run Floyd-Warshall on the same graph that we created, and then we get back some distance. Now we're looking for a situation where the distance from I to I is less than 0 for any I. So it's a diagonal. So we're claiming that the implementation of Floyd-Warshall we have, the diagonal represents our cycle, and if it's less than 0, then it's a negative cycle. And the negative cycle indicates the presence of such an anomaly. Our algorithm returns true if a negative cycle exists. And this works because a truth of Floyd-Warshall is that it returns a negative path cost for a vertex to itself if and only if that vertex has a negative cycle to itself. I don't actually know if that's true on how Floyd-Warshall is presented. I know that for some implementations of it is, but let's see. If not, then maybe we'll have to come up with a different answer. But bundle task here, determining which implementation of Floyd-Warshall this is. All right, so it's going to set the distances between all I and j to infinite, including to itself, right? Because I and j are separate loops, so distance of 1 to 1 would be, on the first step would be infinite. Then it's going to go for all edges. It's going to say the distance from I to j. So all edges that exist is the length of that edge. And then from I to n, from 1 to n, from 1 to n, from 1 to n, it's going to be a minimal distance of k minus 1, distance kj k minus 1, distance ij k minus 1. So this particular implementation doesn't seem to handle when a vertex equal to itself differently than anything else. And so the minimum distance from I to k plus the minimum distance from k to j and the minimum distance to itself, this does seem to indicate that it can go below 0 because these two could be smaller than the distance it already has. So I'm inclined to say that this will work the way I expect it to. Other TAs might disagree. Let's see what the black box post says. They might explicitly state it does something different. I don't want to lead you astray by just like assuming things. I'll double check. Do we say anything? Floyd-Warshall says a 3-dimensional containing the first index iteration's shortest path from the second index to the third index. For example, blah, blah, blah. This table contains iterations 0 through n. So the common use here is negative cycle detection, which I feel like this would be the way to do it. Tim, are you here? Do you want to correct me if I'm wrong on this? Is Tim still here or did Tim leave me? Tim's still here. Tim, does the diagonal contain would the diagonal tell me if a negative cycle existed or will it not?
I don't remember exactly. I do remember we have issues with Floyd-Warshall between the lectures and textbook having some minor disagreements on the order of indexing.
Okay.
Regarding the diagonal, I would defer to the black box post if it says anything about this.
It says it detects negative cycles, but it doesn't say how. I feel like based on the algorithm as in the book that it would, because it would right here consider itself, right? D of ij itself, and then it would consider I to k and k to j. And so if this is some path, shortest path, and this is some shortest path, and it considers the path from I to j where where j equals I, so to itself, and if you find a negative cycle, this would replace it because it's a minimum. And since here we're not explicitly saying that I and j can't equal the same thing, I think this would update the diagonal, is my thought. Because this starts off as infinite and it'll just keep going down. I don't see why it wouldn't update itself if it found a cycle. So I'm gonna go with that. And if you do that on the test and you get it wrong, I will fight Jamie in hand-to-hand combat for you. All right. I'm Soto. Your hand went down. Mahmoud.
Hi. Just because Tim is here and we were talking about this earlier in the chat, if we run Floyd-Warshall and there's a loop from like A all the way back to itself, there's a cycle from A. On the diagonal, would it show infinity, 0, or would it show an actual distance? Because we were all kind of having that conversation in the chat, so wondering what Tim would have to say or what you would have to say about that. I know you said you might not say anything about it, but I'm curious what Tim has to say.
I think the diagonal is the shortest cycle to itself because it starts at infinity and it gets updated by these loops. And I have yet to see a reason why it wouldn't get updated when it finds out that that I can get some distance from I to k and k to, and from I to k and k to j. And if j equals I, I'm basically saying from I to some k and then k back to my current vertex I. And if I find a smaller path than this, which was set to infinity to begin with, this would be my my shortest cycle from I to itself.
Yeah, thank you.
Yeah. I don't see anything that would indicate that it does not. Yeah, because like if there's a separate for loop that says distance from I to I is equal to 0, right? That means that I have established that my path to myself is 0. And therefore, if there's a shortest cycle involving me, that would not update my 0 because that shortest path, unless it's negative, right? That shortest path, shortest cycle to myself would not update my distance to myself. But because the distance to myself is initiated as infinite, because these two are completely separate loops, if I equals 1 and j equals 1 at the same time, then distance of 1 to 1 is infinite. And so I'm looking for a min, and that would update what I think is the shortest distance to myself. And so the shortest distance to myself should be defined as the shortest cycle to myself. And if the shortest cycle to myself is defined that way, then if that shortest cycle to myself is negative, then I have a negative cycle to myself. Okay.
Understood. Thank you.
Yep. All right, cool. Any other questions about this particular problem?
Yeah, I had a question.
Yeah.
So for this one, right? Like, I just want to confirm, is the graph fully connected?
I would think so, right? The way this question is phrased, let me double check. Various currencies, for example, blah, blah. For any two currencies, CI and CJ, there is an exchange rate RI and J. So there is a edge determining what that exchange rate is between any two currencies. So this graph is a fully connected graph.
Okay, so my thought was if we run Bellman-Ford from S, right? Since every vertices is reachable from S, we'll be able to find all the negative cycle.
If you run it from S, yes, I suppose that would be no. Shoot, let me think. So these are directed graphs. Yeah, because it's fully connected, and so there is it's a single SEC. So S would be able to see every cycle that is part of. Although maybe not. Hold on. So I think S can see every negative cycle that it participates in, but it may not participate in a negative cycle in a directed graph, right? So even though S can reach I guess it has to, right? Because if A, B, and C participate in a negative cycle, because A has to have a way to reach S because everything is fully connected, then S would be able to see that its distance to A is updated because this is a negative cycle, and it would constantly So it would be able to yeah you could do Bellman-Ford on this, and then the runtime would be the same because if the idea of running Bellman-Ford on this works only because the graph is fully connected, then it's O of nm is equal to O of v cubed. So that would also be fine.
Okay, thank you. Just wanted to confirm.
Yeah. It would be very hard to find the anomaly, but I guess this question is asking if the anomaly exists to begin with. User graph detecting. Ooh, that is a weird way to phrase it. So if we were to give this problem, we'd phrase it better. But detecting the presence of such an anomaly can mean true or false, but it can also mean find out whether find out where that anomaly is. Yeah, I would say that Bellman-Ford could do it. Yeah. Any other questions? Yep. All right. So I think I would like to add a second office hours tomorrow. I think the next one will be only about maybe 2 hours. I will go over the MST and max flow problems, and I will also go over any exam tips or tricks. So I think I am going to set the next office hour at 7 p.m. Eastern tomorrow, and try to wrap it up by around 9 p.m. If you can't join, sorry, but you can just watch the office hour replay, hopefully. All right. Any questions about the problems I've covered today? Is that Anika?
Is it okay to ask a question about 4.20? I know you went over it before, but
yeah. 4.20.
Yeah, there were some comments on Ed about that problem. I just want to know if that was the right thinking or not. So one of them was saying that you also need to compare it to the distance to V. and distance 2 from U, and I want to see if that's actually required. Let me just put the comment in the chat. Like, is that something we need to consider as well, or is it okay to just take the minimum of what you have there?
So we've had this discussion within the TA team before, and
Okay.
we would give you the benefit of the doubt in the sense that if we cared deeply about the direction of, the head and tail of where your checking is, an adjacency list technically lists the each edge twice, and so because of that, it technically would take care of it from either direction because it would be considered twice. Like for each edge that you're doing UV of, there would be a corresponding edge of VU to be also considered. So generally, we wouldn't care. Like, I think the last time a similar problem came up, the decision was if you didn't go out of your way to break it, we would just assume that it works based on how I wrote this. But if you went like really out of your way to like do some really like tricky stuff and it broke completely, then you could lose points for it. In general, when you're given a undirected graph, just work with it as an undirected graph. You don't have to like think too hard about like, oh, what if I came in from this direction rather than this direction? Like you can just treat it as like a undirected graph and leave out some of those like edge case details.
Okay, and then the other one was, do you need to also consider if the original path from start to finish was shorter than us adding something to it?
Yeah, so like I said, we would typically in our problem explicitly say that if you have to handle that or not. When I answered this question, it wasn't part of it, so this is where my note is. Like if there exists a shortest path from S to T and G already, it would be trivial to figure that out, and I give a little bit detail about that, but I didn't want this to be like a main part of my algorithm.
Cool, thank you.
Yep. Spencer?
Hi, I was wondering if I could ask a question about something you said in the Monday office hour, or last Monday, I guess.
Okay.
So I think the context was around question 4.14, involving strongly connected components. And something you stated there kind of confused me. I'm not sure if you were, well, let me say it. I think you said something like a strongly connected graph means that all vertices either have a path coming into it or a path coming out of it. To me, that confuses me a little bit because I believe like a strongly connected graph would have to have an incoming and an outgoing edge to every vertice. Is that correct?
A strongly connected graph means that it's the entire graph is a single SEC, which means that all vertices have incoming and outgoing edges.
Okay.
Because yeah.
Okay, so we agree.
I don't
think
remember what
maybe
I don't
the
remember what I
context.
said exactly. Yeah.
Okay, I think the context was you were maybe describing the difference between like a strongly connected graph and like a connected graph or something like that. So I think I may have just gotten some wires crossed there.
Yeah.
I do have one other question involving that that question. I believe it's the graph is strongly connected and you want to get the shortest path through a vertex on that question.
Okay.
I was curious. So we know that it's strongly connected, so there's a path from every vertex to every other vertex. Now I had made the claim, I believe that in a discussion that after we make the statement that every path has to go through vertex X, that you no longer can make the claim that it's strongly connected. So like if you had for instance, if you had a graph that went from, it's like a cycle essentially, A to B, B to C, C to A. Sorry, I'm trying to form my question here. It's hard to.
Hold on. Alright. We are looking at a graph and we want to say like that?
Yeah. Yeah. So if you say that a path has to go through B, is it safe to say that there is no path from C to A through B? Given the definition of a path, meaning there's like no cycles, because that would be a walk.
So we want to find for every pair of vertices, I want to find
a path.
So okay.
Find all
so you're
paths
saying,
through B, essentially.
Right. So you're saying I need a path from C to.
I guess my question here is there's a path from A to C through B, but is there a path from C to A through B? Because it's in my reasoning here is that there isn't a path from C to A through B, because it would make us you would have to go from C to A to B, then back to C, right?
Yeah,
and that would
hold
mean
on.
you visited the same vertice twice.
I feel like we wouldn't hear about this edge case if we were to grade it. I don't think that's the intention of the question, and I think if you handled it, we would accept it, and if you didn't handle it, we would also accept it.
Okay, so it's like a light definition of a path, because I think the strong definition of a path means you can't visit the same vertex twice.
Yeah.
I know I don't think this would be specific scenario would like come up on an exam question.
Yeah, no,
but
I think it's a fair question that you're asking. But I think, yeah, I think, yeah, I mean, by the purest definition of path, the edges have to be distinct and the vertices have to be distinct. So you could potentially end up with a situation where that wasn't possible, even if it's strongly connected. And I think if the strongly connected part wasn't there, we would assume that's what the author meant, is that they want you to handle whether there would be a path or not. But the fact that it is strongly connected makes me think that, like, yeah, they think they believe that there is a path between a proper path between all pairs of vertices through B. I think the way we would give this question, if we were to do it, it would be to say, find the shortest path all through between all pairs of vertices through V0, but assume that that all those paths exist. I think is the clarification we'd give. We also wouldn't ask you for like the pair, because it kind of blows up the runtime. There's a lot of ways I would rewrite this problem, but I think it's a fair question to ask. And it would be unfair for us to be like, aha, we got you. You didn't think about it that way.
Gotcha.
I would ask the grading team not to give a penalty on that.
Okay, thank you.
Any other questions? All right, so that concludes our first half of our exam office hours. Like again, I will continue the second part tomorrow. It will likely from 7 to 9 p.m. I will cover MSTs, max flow practice problems. I may have like one or two advice on exam itself. Okay, thanks everybody.
Thank you, Joves.
Thank you, Joves.